Я же снова на батарейке. К концу лекции сгибается.
Что?
Спокойно.
Да?
Для участников молчи, но хотя бы микрофон.
Сейчас я возьму мелку.
Okay, are we ready? All right, so let us continue with lecture number 4 by Pasha Yetingov.
All right. So, last time we discussed the Hitchin integrable system, and we proved the Hitchin's theorem that this system was integrable in the case of GLN or SLN on a curve of genus greater or equal to 2. So today I want to compute some examples. But the problem is that computing for curves of genus greater or equal to 2 is rather difficult because the band G in that case is pretty complicated, and it is hard to write down coordinates. One can do it. In fact, Turin did it, and for GL2, and Krejcir did it, generalized it to GLN. So one can do it, but it's rather difficult. So we will actually consider a generalization of Hitchin systems when you have punctures on your curve. And this will allow us to have non-trivial situation when genus is 0 and 1. And those things will be amenable to explicit computation. So, so let me talk first about bundles with parabolic structures. So first, suppose we have H inside G, a subgroup, closed subgroup, and suppose we have E, a G bundle on X. So at this point, this is very general. You can take any variety, any algebraic group. And so we say that so if you have a point X in X, then definition an H structure at X is an H orbit in the fiber EX. Recall that EX is a torsor over G, so it's essentially a copy of G where we forgot the position of the origin, but still we have a simple transitive right action of G on the fiber, and we want to take an H orbit. And so how many possibilities we have? So how many choices do we have? Well, clearly it's parameterized by the quotient G over H. Because it's our essentially H cosets, right? Let's say H cosets on G. And now we're in particular going to be interested in the situation where H is a parabolic subgroup. So let's fix some points, T1 to Tn are points on our curve X, distinct points. And P1 through Pn. By the way, I should say that when we talk about H structures, well, H matters only up to conjugation. Well, in the sense that if we have an H structure, which is an H orbit, and we multiply on the right by some group element G, this will transform an H orbit into GHG inverse orbit. And so suppose these are parabolic subgroups. So parabolic subgroups, so I remind you that G is a connected reductive group, for example, GLN, and parabolic subgroups means they contain Borel subgroup. So these are the subgroups for which the quotient is a projective variety. Connected, yeah, there are subgroups for which the quotient is a projective variety. For example, for GLN, if you have a composition n equals to n1 plus n2 plus n r, then a parabolic subgroup corresponding to this composition is the set of all matrices of this kind of form. So this is n1. So this is the corresponding parabolic subgroup. It is the subgroup of matrices with this block structure. In particular, the smallest parabolic subgroup is the Borel subgroup, which is the upper triangular matrices. Okay, so and so now I want to define Ban G of x, T1 up to Tn. So there should be the same. So each choice of parabolic subgroup corresponds to the corresponding point. So P1, Pn. So this is the moduli stack of G bundles on X with Pi structure at the point Ti for I equals 1 through n. So at every, you should think about this picture here. So you have your curve, then you have your points, let's say T1, T2, T3, T4, and then you fix parabolic structures at those points. Parabolic structures are structures corresponding to this group. For example, so the basic example that we are going to consider is, let's say, G equals to, well, GL2 or PGL2, and Pi are the Borel subgroup, which is the subgroup of matrices of this form. And in this case, so how can we think in general about, so I said the choices are, the set of choices are G mod H, but it's not canonically G mod H. It's isomorphic to G mod H. So more precisely, what happens in this case, so suppose if G equals to GLN, then what is the fiber of a point of the bundle E at the point X? So we said that in this case, G bundles are the same thing as vector bundles of rank n. And so suppose we have some bundle E, so it's a rank n vector bundle. Well, then what is the, so it has some fibers. So what is the fiber? So the E, let us write a script E to be the corresponding GLN bundle, principal GLN bundles. So we said that they were corresponded to each other, but the fiber of this is a vector space of dimension n, and the fiber of this is the general, a torsor over the general linear group. So what is the fiber of E at a point X? Well, it's actually, it's isomorphic to GLN, but what is it canonically? Well, I claim that canonically it is just a set of all bases in the fiber of the corresponding vector bundle. The set of all bases in a vector space is a classic example of a torsor over the general linear group, because we can make change of bases by a matrix. And so, so that's the fiber. And in particular, if P is a parabolic subgroup, so if P is a parabolic subgroup, then what is a parabolic subgroup? Like I said, it is a subgroup of this form, so it preserves a partial flag. Stabilizer of a partial flag. 0 is contained in V1, contained in V R, which is equal to V, where the quotients have the dimension. I ran out of space. Okay, so let me write here. So the quotients Vi plus 1 over Vi have dimension Ni, corresponding block. And so then the fiber of the corresponding a P structure at a point X is the set of bases compatible with this flag. So this means that there is a subset of the basis which is a basis of each of the spaces Vi. That's just basic linear algebra. And so in particular, in this simple situation, well, fixing, well, with a flag. So a P structure is the same as fixing a partial flag. So that's a convenient way to think about P structures. It's a fixing a flag in the space E sub X. Partial flag with quotients having dimensions Ni. And so in particular, in this case, we have just a two-dimensional space, and we have a complete flag, but fixing a complete flag is just fixing a one-dimensional subspace, a line in Ex. So a parabolic structure, B structure on some vector bundle E, rank 2 vector bundle. So let's talk about vector bundles. It's technically a bit easier. Is just at a point X in X is just a line L inside Ex. So this means that we are fixing a line at every. So we have these fibers Ex, ET1, ET2, ET3, ET4. They are two-dimensional spaces, and in each of them, we are fixing a line. And our moduli space or stack is just the set of all such data. So this shows that. Question? Okay. So we have a fibration from bond G of X T1 through Tn, P1 through Pn into bond G of X with fiber G, so flag manifolds, partial flag manifolds G over P1 cross G over P2, G over P. Okay, and so so why do we want to consider this? Because the problem, well, first of all, it gives us a more general theory, but specifically, I want to consider it today because that allows us to consider genus 0. Remember that we started last time, we considered genus greater or equal to 2, and there was a good reason for it. That in genus 0 and genus 1, if you don't have marked points on your Riemann surface, you do not have stable bundles. All bundles are going to have non-trivial automorphism groups, even if your group G is adjoint and semi-simple. If your group is a semi-simple and moreover adjoint. And so we weren't able to, and what we need is we want to have generic bundles or stable bundles, which are, roughly speaking, bundles with trivial or finite automorphism group. However, if we put more data, we put these points here and we put these lines, then automorphisms will have to preserve this data. And the automorphism group will become smaller because we're putting more conditions on automorphisms. And in particular, there will be a lot of bundles that will have automorphism group trivial. So in particular, if n is at least 3, then a generic bundle on P1 with parabolic structures has trivial automorphism group. So we have a notion of stable bundle. So there is a notion of a stable bundle with parabolic structures. And there are actually more than one, but it doesn't matter much which one we will use for the purposes that I want to discuss. And let me not discuss this right now. Maybe if we have time, I will explain what this means. But basically, you can take just the trivial bundle. So let E be the trivial bundle. And in this case, the automorphism group of E. So let's talk about PGL2 bundles. So which means these are vector bundles of rank 2 modulo tensoring with line bundles. So the automorphisms is just the group PGL2. Because we just have the trivial bundle. All the fibers are canonically the same. And that's because a holomorphic function on a compact Riemann surface has to be a constant. So, but then, but we have parabolic structure L1 through Ln, where Li, all of these Li lie in the projectivization of the fiber of E at the point Ti, but all these fibers are the same. They're just C2, so this is just P1. This is standard P1. Yes? So there is a notion, so we have a notion of a principal vector bundle. Automorphism of a vector bundle is a so this means there are many ways to think about it. So one think of it is it's a section of E tensor E dual, which is non-degenerate at every point. Another way to think about it is on every open set where the bundle trivializes, it is just a regular map from this open set to GLN, such that these maps agree on the intersections through the clutching maps, and so on. So there's automorphism. Any kind of structure we define, there is a notion of automorphism. So in particular, for trivial bundle, automorphism is a holomorphic function on the entire X with values in GLN, which is a matrix-valued function with a determinant non-vanishing. But of course, such a function has to be a constant because our Riemann surface is compact. And so we just get a matrix. Right, exactly. So actually, there is a whole point on this Hitchin story, which comes from differential geometry rather than algebraic geometry, where you actually define the Hitchin moduli space not as a cotangent bundle to bund G, but as a space of solutions of certain PDEs, which are called Hitchin equations, and which are the Young-Mills equations for the two-dimensional gauge theory. But we are not going to discuss this point of view. Questions? Okay. So we get an action. So PGL2. So the set Bon G of X T1 Tn P1 so let's say when I have Borel subgroup, I'm not going to write my P's. And so the set, let me write triv, parabolic bundles with parabolic structure, which are trivial as just vector bundles. So this set is just, it's an open subset in the whole stack because generic bundle is trivial. Well, it is just P1 to the power n quotient by PGL2. So this is a much more explicit space on which we can do computation. Note that this is still a stack because there are some points here. So this is just collections of n points, but there is still stabilizers. For example, if all points coincide, there is a stabilizer of a point on P1, which is the group B of upper triangular matrices. Yeah. So, but inside this contains an even smaller open set. Of tuples of points y1, yn. So here there is some vector of points y1, yn, where let's say y1, y2, y3 are distinct. And it is well known that PGL2 acts simply transitively on triples of points on P1, which are all distinct. So in particular, this subset is just so we can, there is a well-known theorem that if you have 3 points on P1 which are all distinct, there is a unique element of PGL2 that maps it to 0, 1, and infinity. And then, so we will get that this open subset is just P1 to the power n minus 3, because there will still have the other points. But we no longer have any stabilizer. We no longer have any group acting, because we killed all the symmetries by making the first point 0, the second point 1, and the third point infinity. And this is already a variety. Okay. So, but this, so we are going to live basically on this stack. I mean, it is slightly stacky, but you know, it's much simpler than the general thing. And we will be able to do calculations using these coordinates. So this yi are going to be in P1, which is C union with infinity, Riemann sphere. Okay. So in general, bond G with trivial as an abstract bundle of X, T1, Tn, P1, Pn is just the following space. It's the product over I of the flag manifolds G over Pi and quotient by the diagonal action of G. So this is still a stack, but it's much simpler than the general stack of all bundles. So now I want to so we can still talk about the Hitchin system. So the next thing is Hitchin system with parabolic structure. And it generalizes rather straightforwardly because, so remember that Hitchin system was constructed by realizing the bond G as a double quotient and descending a certain collection of Hamiltonians upstairs on the cotangent bundle of the loop group down to the double quotient. Well, we can still represent it as a double quotient here. So double quotient representation of bond G, T1, Tn, P1, Pn. Well, it's actually quite easy to do. So recall that bond G of X is just double quotient G of, so let me realize it. So I explained that there is a realization when we take out these points, T1 through Tn. So let Zi, Z1, Zn are local coordinates near, well, maybe I don't need even to introduce coordinates. Let me just work canonically. So, so this is a product over I of G of the punctured disks around the points Ti over the product over I of G of the ordinary disks non-punctured, and on this side G of X minus T1 Tn. So that's the usual bond G. But now, if we want to fix parabolic structures, then of course, this is the data at the points Ti. And so this group of all functions on the disk Ti around Ti. So we have this picture here. Again, we have points T1, T2, T3, and T4. And then we have these infinitesimal disks around them, DT1 and so on. And we're using two charts. One chart is the union of those disks. The other chart is the complement of these points. And so the parabolic structures are local structures at the points Ti. So this means that we have to change something on this side. And in fact, it is clear what we should do. So we have a homomorphism from G of D to G, which is the evaluation map, evaluates it at the center. So evaluation of G of Z is just G of 0. Evaluates a function on the disk at the center. And then we can define the groups Pi tilde, which is pre-image under this map of the parabolic group Pi. So in other words, it is all Taylor series where values in G, such that the constant term lies in Pi. And then we just see that bond G of X T1 Tn P1 Pn is simply the same thing, but with these groups replaced by the pi tildes. So it is the product over I, G of dx dti times over the product over I pi tilde, and on this side, G of x minus T1 Tn. This is clearly fibers. So this statement here, that we have this fibration over there, is clear from this presentation because we just replaced the product of G over dti by product of pi tildes. So the error we make is the discrepancy will be the product of quotients of these groups by those, which is the same as G mod pi, because the only difference is in the constant term. Okay, so we've got that. And so now we can take the same Hamiltonians pi of phi on cotangent bundle of this loop group. So we did it for one puncture, but the same thing works for any number of punctures. And so, so cotangent bundle of G of dt1, cotangent bundle G of dtn, and do reduction, Hamiltonian reduction with respect to G of x minus Ti times the product of pi tilde. And then we obtain an integrable system on bond G of T1 Tn P1 Pn. So one can show that Hitchin's theorem extends to the setting. Huh? On T star, yes. So as before, so we have infinitely many. So these are actually infinitely many. So this is HIN, which is a residue of this multiplied by Zi to the n. And so there are infinitely many Hamiltonians here. They descend to here. They become linearly dependent. But still, the remaining ones, which are independent, come in the right number and form an integrable system. So I'm not going to prove it, but we will compute what happens in the example of GL2. So what will we get then? So what is this thing here? Well, this is the set of pairs E phi, where E, we know what it is. E is a parabolic bundle, which is a bundle equipped with parabolic structures. But what is phi? So phi is a Higgs field. But, of course, now we have a bigger space of E's that is bigger by the product of the flag manifolds. So it has bigger dimension. So we should also have similarly bigger space of Higgs fields, because it has the dimension has to increase by the same amount. So this means that it's not just enough to take Higgs fields for the bundle E. So we actually should allow singularities. So that previously Higgs fields were just holomorphic. But now we should allow singularities at the punctures. And so you can check that the correct condition is the following. So with singularities. And the condition is the following, that phi has at most first order poles. So remember, phi is one form with values in the endomorphisms of E. One form on X with values in adjoint bundle of E. But it is now can be singular at the points Ti. And so it has at most first order pole at the points Ti, and the residue strictly preserves the flag Fi at the point Ti. So remember, specifying a parabolic structure means that we specify a flag at the point Ti. So Fi is a flag in the fiber. But strictly preserved means it's a Lie algebra element. That's right, yes. So this means it lies in the unipotent radical of the stabilizer. Lies in unipotent radical of the stabilizer of Fi. So in particular for usual flags or partial flags for GLN, this means flag is a filtration on our space, and strictly preserved means that it maps I space of the filtration into I minus 1 space. So it acts by 0 in the associated graded. Which group? Yeah, it acts freely on some open set. So like I said, that there will be lots of generic bundles with trivial group photomorphism. So the stabilizer, so if you represent something as a double quotient, this means that this product of these groups acts on this group. And the stabilizer is the basically intersection of this with the conjugation of this. And this will be exactly the automorphism group of the bundle. So in this case, with parabolic structure. So for generic bundles, it will be trivial if we put enough points, even in genus 0. Other questions? Okay. So now, so this is an exercise to check that this is the right condition, because of course we discussed that cotangent bundle of bond G is a H1, a certain H1 group of X with coefficients in the adjoint bundle. So here this will have to be amended somewhat by considering singularities. So maybe I should call this as an exercise. But this is the correct condition. So in particular, for PGL2, so phi has simple poles at the points Ti, and phi and residue of phi at the point Ti is nilpotent and acts by 0 on the line Li inside the fiber of E at Ti. So, by the way, when I talk about residues, you might object and say that, well, we can only talk about residues of differential forms. Well, in our case, it's a differential form with values in some bundle. But of course, when we take residue, we obtain just a section. We have just obtained an element of endomorphisms, and so this makes sense. And in fact, it doesn't even matter because when we for this condition, it matters only up to scaling, so it really doesn't really matter. Okay, but so that's the condition, and so let's compute now. So now let us compute the Hitchin system for PGL2 in genus 0. And so for this purpose, we will assume that the points T1 through Tn actually belong to A1 inside of P1. So they're just complex numbers, just for the convenience of computation. And parabolic structures at Ti is going to be Yi. Well, again, it's in P1, but I'm going to assume that it's in just in A1. So this means that I take Yi corresponds to vector Yi1 in C2. And the line Li is spanned by this vector. Okay, so now, so what is a Higgs field now? So Higgs field is a one form with simple poles at Ti valued in SL2. So this means that phi is going to be the sum of over I from 1 to n of AI divided by z minus Ti times dz. But it should be regular at infinity because we don't have, and so these AI are in SL2. And then it should be regular at infinity because at infinity we don't have a puncture. So a form like this is regular at infinity if the coefficient of dz has a second order decay because the form dz over z, for example, is singular. Dz over z squared, dz over z cubed are already regular because dz over z squared is differential of 1 over z up to sine. And so this means to have a condition that the sum over I of AI equals to 0. Huh? Yeah. I'm not done yet, of course. All right, and then so also we want these residues, AI, they should be nilpotent, and they should kill the vectors yi1. So let's compute what that means. So suppose you have A nilpotent and kills the vector y1. So A is equal to A, B, C, D. And so we've got A, B, C, D times y1 is 0. So we've got AY plus B is 0, and CY plus D is 0. Okay, so we can compute everything in terms of C. So first of all, D is minus A, because we need trace 0 for nilpotent matrix. B equals to minus AY, and D equals to minus, So d equals to minus cy. So this means that a equals to cy, and d equals to minus cy. So we've got that a is cy minus cy, and then b is minus ay, but a is minus a is cy. So we've got this is minus cy squared, and finally this is just c. And so this means that for each I, I'm going to have ai is equal to, well, let me call, in this case, c by pi, because it turns out that these, so yi are coordinates on our space, and pi are momentum variables. It turns out that they are canonical coordinates. So the symplectic form will be sum of yi dpi. And then ai is going to be pi. So there is an overall factor pi. And here is going to be yi minus yi squared minus yi and 1. Okay? So we see now we still have an PGL2 symmetry. I did not kill it. So this means that we will write some system in terms of these y's, and then we should take reduction with respect to PGL2. So it will be invariant. This system that we will get is projectively invariant. I could kill it, but then the computations would become more ugly. So it is better to keep it in the game. And so this way we have n phase space of dimension 2n. We have n y's and n p's. When we do complete reduction, we will get, as I said, n minus 3 dimensional space of y's and n minus 3 dimensional space of p's, but the formulas will get ugly. All right, so let's compute our Hitchin Hamiltonians. So in this case, we only have quadratic ones, right? Because we have PGL2. So we have H N2, which is, let me write 1/2 of the trace of phi squared. Well, we can calculate what this is. This is 1/2 of trace of the sum of ai over z minus ti, aj over z minus tj for I and j. But now I equals j drops out because ai is nilpotent, so ai squared is 0. And of course, the terms with ij and ji are the same. So we're going to get the sum over I less than j of trace of ai aj divided by z minus ti times z minus tj. And so, well, of course, everybody knows that we have this identity 1 over z minus a, 1 over z minus b equals to 1 over a minus b, 1 over z minus a minus 1 over z minus b. And so this can be written, therefore, as the sum over I different from j, trace of ai aj, or ti minus tj times z minus ti. Okay, so now it remains to calculate this trace of aiaj. So the trace of aiaj is pi pj times the trace of what? Yi minus yi squared, 1 minus yi times yj minus yj squared, 1 minus yj. And we only need to compute the diagonal elements. So we've got pi pj, and then what? Well, we've got yi yj minus yi squared plus yi yj minus yj squared. So this is equal to pi pj with a minus sign times yi minus yj squared. And so, so now we, well, remember this is a function of z, so there are infinitely many integrals. But we can extract integrals by taking coefficients of that with respect to z. In particular, here we can take residues. By the way, this is, I should write here the dz squared, which I have skipped because it's a quadratic differential. And in particular, we can take residues at the points ti. So, so let's take gi to be a residue of h n2 at the point ti. So at this point, we have trivialized everything. So we can take residues of quadratic differential functions or anything we want. So this is equal to what? Well, it's just a value, just the numerator here, which would be I is fixed. And so this is going to be the sum over j different from I, pi pj yi minus yj squared divided by tj minus ti. And so we obtain an integrable system with integrals like that. And this is the so-called Garnier system. Okay, any questions about this? Can you speak up, please? How to take residue? It doesn't matter. At this point, I trivialized my coordinates. It doesn't matter. I mean, okay, if I change coordinates, it will multiply by a scalar, but it will still be an integral of this flow. I'm just writing down some. So this thing is basically a generating function for integrals of my flow. And so, so there are n integrals here on a phi space of dimension 2n. The sum of these gi's will be 0, but when after reduction, this will become an integrable system. Because it has symmetries, so after reduction, we will have integrable system. Yeah, for the trivial bundle, we took the chart where the bundle is trivial because generic bundle is trivial. So then the question is what happens, for example, when we come to certain singular points, so this flow extends to a bigger space. And that's an interesting question. This is an example of when integrable systems initially defined on some simple space extend to a bigger space. But I'm not going to discuss this. Yes? Well, there will be additional coordinates corresponding to moduli of the bundle E. So here we use the fact the generic bundle on P1 is trivial. That's no longer the case even for elliptic curve and also for higher genus. So there will be parameters of G bundles. And so we will still have to have coordinates corresponding to variation of G bundles. And the story will become much more complicated. You can still write things in Turing coordinates, for example, but it's going to be much more complicated. Yes? No, this is just a, in this case, it is a sum of simple fractions. It is sum of something independent of z divided by z minus ti. So I just take the residues of this thing. It's already expanded in partial fractions. Yes. Yeah, you can compute what happens. So parabolic points can collide. And then what you normally get, well, if you want to get some interesting answer, you should also do twisting, which is what I will explain in a second. But in that case, you will obtain some confluent versions of this system. Yeah, there will be some integrable systems which are obtained by limit of this. We should consider Garnier system with parameters, which I will do in a second. And then these if you collide points and simultaneously send corresponding parameters to infinity, you will get interesting limits. Yes. Oh, well, some open set there is p1 to the power n minus 3. Well, here we're working on p1 to the n, or rather a1 to the n. So our space that we're working on is really T star of Cn, because we didn't kill the SL2 symmetry. So we only took reduction with respect to, let's say here, with respect to the group. So we took here functions which vanish, which are equal to 1 at infinity, so smaller group. And then to get the full picture, to get down to the actual Hitchin system, we have to do another step of Hamiltonian reduction by PGL2, by G. And we did that in order to make formulas nicer. So now you can compute. So there is this integrable system. So on this thing acts the group PGL2. And you can take a reduction with respect to that group of this integrable system, and you will obtain an integrable system on n-3 dimensional space. And you can compute the Hamiltonians, but the formulas will be less nice. No, not, well, you see, it's this. So actually, here we also, I lied when I said that we have an integrable system here, because the sum of these gi is actually 0. The sum of ti times gi is also something fixed. The sum of ti squared times gi is also something fixed. So this means that we have 3 integrals fewer than we want. But instead we have a SL2 symmetry. And so, so we can kill it, and then we will get a true integrable system. So that's a more honest way of explaining it. Well, again, this is something that is easier maybe to say if we consider some deformation, which I am going to explain. Yes. Do we have the same? Yeah. That's what I'm going to explain. There is a twisted version where we don't require them to be nilpotent, but rather they have a certain particular eigenvalue. Yeah, I'll explain. That's what I was going to explain. Other questions? Yes. Very loudly, please. Yes. I'm sorry, I didn't Well, they are tangent, they are basically cotangent bundles. So we have these flag varieties here, and these correspond to elements in the cotangent space to the flag variety. In this case, we do not have moduli of bundles themselves. We are considering trivial bundle, and everything comes from these flag varieties. Okay, other questions? All right, so I will now explain a twisted version. Actually, I don't want to erase this, so let me just erase this here. So the twisted Hitchin system. And for this purpose, I first have to explain Hamiltonian reduction along orbit. So I explained that if you have, let's say, M, a symplectic manifold, we talked about cotangent bundle, but more generally, just any symplectic manifold, and you have a group H acting on this M, then we have suppose we have a moment map from M to H dual, and this is in general, it's just a piece of data. It doesn't always exist. Well, then we can define this reduction, mu inverse of 0, modulo H. This is the Hamiltonian reduction, which we discussed. And if the action is nice, if H acts freely, in nice cases, this is a symplectic manifold. Well, this has a generalization. We actually can take pre-image not of 0, but of any invariant, of any coadjoint orbit of H star. More generally, can consider mu inverse of O over H, where O in H star is an H orbit. So any coadjoint orbit has a canonical symplectic structure, which is a so-called Kirillov-Kostin structure. So using this, you can check that this will also have a canonical symplectic structure. And so, in particular, and then you can do so we can run the same story. So we can run the same construction with integrable systems. So if you have some functions fi in involution on M, and fi are H invariant, then they descend to functions fi bar on this reduction, mu inverse of O over H, which are also in involution. And the proof is the same, actually. So, and sometimes you have, too few functions upstairs, but when we go downstairs, you have just the right number. And we can apply this procedure to, so this gives us a more general class of integrable systems, and in particular, we can apply it in the setting of Hitchin systems. So we can do reduction along orbit. So for example, in this situation, we have product of G of disks dTi punctured, and inside here we have G of x minus T1 Tn times product of G of dTi. So we can take we can do reduction. So reduce first by so this maps to the G to the power n by evaluation at T1 through Tn. And there is some kernel K of this evaluation. Let me call it ker. So we can first reduce by ker, and then get a residual action of the quotient group, which is this. And then we can take some orbit O inside G star to the n, and then we take mu inverse of O over G to the n, and descend Hitchin Hamiltonians to this quotient. And so this procedure means, so let's see what this procedure does in the case of PGL2, which we have played with today. No, at the moment there aren't. We will see how this is related. So parabolic structures will be related to the case when we take this to be the biggest nilpotent orbit. Huh? No, just any, well, I mean, you need some sort of freeness of the action. But as long as it is free, then this will work. Okay, so let's see what the condition will be. So this should create some condition. So this mu inverse of O modulo G to the n will be the set of pairs E phi. But the condition on phi, so this will be some sort of twisted cotangent bundle of parabolic bundles. But so let me just explain what the condition on phi will be. So the condition on phi will be that it's going to be so I'm going to so we still have so let's take G equal to PGL2, and then orbits. So we have to fix orbits, coadjoint orbits for G dual for all points. So so orbits in SL2 dual, which is SL2, will be at the points Ti. We will fix the orbit lambda I 0 0 minus lambda I. So let's say we have this orbit for generic number lambda I, which is not 0, let's say. So then the condition on phi will change. So the previous case also corresponds. So you can check that the previous case with parabolic structures, ordinary Hitchin, it corresponds to fixing the orbit of nilpotent element, which is a limit of such things. If you put 1 here, it's the same conjugacy class, and then it goes to 1 to this when lambda goes to 0. So the condition on phi will now be phi has simple poles at Ti, and the residue at Ti of phi doesn't kill Li, but on Li it acts by eigenvalue lambda I. This is surjective. What? Yeah, but that's here I'm saying something different. So there is this big group, and it projects surjectively into this. And then I have some kernel. So I can reduce first by the kernel in the usual way, and then I can reduce by this residual group G to the n using an orbit in the coadjoint representation of this group, which is this. This? I evaluate, well, it's this maps to 1. I mean, this ignores this factor. And then for these factors, it just evaluates these at the centers of these disks. Okay, so we've got this condition. So again, phi is going to be the sum of AI over z minus Ti dz. But now the equations will change. So instead of the equations over there, we're going to get that AI times yi1 is not 0, but it's lambda I times yi1. So let's compute what happens in that case. Okay, so we do this calculation again. So A times y1 equals to lambda times y1. And this is A, B, C, D. So we've got A, y plus B equals to lambda y. And Cy plus D equals to lambda. So, so we've got the D is equal to lambda minus Cy. And this means that A equals to minus lambda plus Cy because the trace must be 0. And then B is equal to lambda y minus Ay. So lambda minus A y. And lambda is this. So this is equal to 2 lambda y minus Cy squared. So we've got the following matrix. Minus lambda plus Cy, lambda minus Cy, 2 lambda y minus Cy squared, and then this C. And so this means that the matrices AI are going to be as before, but with this lambdas. So minus lambda I plus pi yi, 2 lambda I yi minus pi yi squared, pi, and lambda I minus C minus pi times yi. And so then you can compute the trace of AI aj. So that's the only thing that will change, the formula for this trace. So we're going to get some additional terms. So we will get some additional terms. So the usual thing, minus yi minus yj squared pi pj. This is without the lambdas. Then there is a quadratic part, and this is going to be twice lambda I lambda j, which is just a constant, so it doesn't really matter. And then there will be the interesting term, which will be 2 lambda I pj minus lambda j pi times yi minus yj. So that would be the correction that we get from the lambdas. And so therefore, what we will get is, okay, so we will get the deformation. So we get the deformations, gi of lambda 1, lambda n is going to be the sum over j different from I. So here is going to be ti minus tj, or maybe tj minus ti. And here is going to be minus y1 minus y2. Yi minus yj squared pi pj plus twice lambda I pj minus lambda j pi times yi minus yj plus twice lambda I lambda j, like this. And so that's a deformed or twisted Garnier system. But the problem is, so okay, so when you take the trace, okay, so I used before that ai square is 0. Now I square is not 0. Now a square is a scalar matrix. Yeah. But that term will only contribute constants, so I threw it away. No. So let's go back. So we have the following function. So there's going to be the sum. So trace of phi, 1/2 of trace of phi squared is the sum over I and j of trace of ai aj 1/2 over z minus ti, z minus tj. I am going to drop dz squared. And so in particular, this equals to 1/2 times the sum of trace of ai squared, which is really 2 lambda I squared, because this is a function that has eigenvalues lambda I and minus lambda I, divided by z minus ti squared. So in this case, we do have a term which vanishes, which has a second order pole at ti. But if we only take the coefficient at ti at minus 2 second power of the coordinate, we will just get lambda, which is a constant. No, they are not interesting because they are not, okay. And for integrable system, they are not interesting because we're trying to construct some Hamiltonians. Constant is not a very interesting Hamiltonian. Yeah, and in fact, this term is also not very interesting. We can drop it out. So the interesting part is everything else. Okay. So now So this is the deformed Garnier system. And finally, I want to explain how elliptic Calogero-Moser system can be, and its Lux matrix discovered by Krichever can be seen as a special case of the Hitchin system. And the previous was what? Yes, exactly. Yeah, so that's a limiting case, which is resonant, which is where this matrix is not semi-simple. And that corresponds to parabolic structure. So then the lambdas are going to drop out. And so that's why that corresponds to what I said before, that ordinary story with parabolic structure corresponds to taking nilpotent orbit, as opposed to a semi-simple orbit. So when we do reduction with respect to a semi-simple orbit, what we will obtain is not the usual cotangent bundle of our space bond, but actually something that's called twisted cotangent bundle. But it doesn't matter at the moment. So let's talk now about genus 1. So X is an elliptic curve. And so what do generic bundles on elliptic curve look like? So let's consider generic bundles, let's say of degree 0, of rank n. Well, they are direct sums of line bundles, but in this case, line bundles have parameters. So, so let's say L. So there is a 0, and there is an L sub A, where A is an X. So line bundles of degree 0 are elements of the Jacobian. Jacobian of elliptic curve is the curve itself. So we have bundles LA, A in X, which is really O of A times O of 0 to the minus 1. And the section of this LA is this function that appeared already many times, theta function of Z minus A divided by theta of Z. So this section is meromorphic. It has a pole of first order at 0. This, for A different from 0, this does not have holomorphic section, but it has a meromorphic section, which is this thing. And this section really defines this bundle. And so generic bundles, and so these generic bundles are of the form E is equal, so Atiyah showed that they have the form, and it's not difficult. They have the form LA1 plus so on plus LAN. And let's say AI are distinct. Okay? So now, so suppose we put a parabolic structure. So let's consider the case of G equals to, let's say, PGLN. And then we put one puncture at 0. And put the, and do the twisted reduction there. For the orbit O inside the Lie algebra. So O is generated by the matrix. So let's put matrix 1, 1, 1, and minus n plus 1. So it's a kind of simplest semi-simple orbit. It is the smallest semi-simple orbit. It consists of matrices which have eigenvalues n minus 1 eigenvalue 1 and 1 eigenvalue minus n plus 1 to balance out the trace to be 0. Okay? So we do reduction with respect to this. No, they're semi-stable. These bundles are semi-stable. There is no stable bundle. ATIA has stable bundles of degree 1. For degree 1, there are stable bundles, but there is only one stable bundle. So, if you just consider stable bundles, you will get the differential equation on one point. It's not very interesting. It's invariant under shift. No, you cannot get anything interesting if you don't introduce this orbit. Okay, so and so this orbit corresponds to really taking maximal parabola. So if you degenerate this orbit, well, I mean, you can put C here. So let's put C, 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 and then minus n plus 1 C. So when C goes to 0, this orbit degenerates to this one. So it's a nilpotent matrices of rank 1. And this corresponds to the maximal parabolic subgroup, which has n minus 1 times n minus 1. Here is 1 by 1. So that's P. So this means flag variety for this case is just projective space, P n minus 1. Because the flag is just a line, fixing a line inside, or if you like, a hyperplane. So it's a projective space. So let's think about it as a set of lines. And okay, so what is the automorphism group of this bundle? So automorphism group of E is the torus, right? Because there is no maps from LA1 to LA2, for example, because AI are different. But there are endomorphisms of LA, which are numbers. And so automorphism of this is C star to the power n. And so this acts on this projective space. And we need to look at free orbits. So free orbit is unique. Well, no, well, it's a PGL. So I have a PGLN. So that means it's that. Well, okay, so there is a free orbit of the vector where all entries are non-zero, and then I can make all of them 1. So that's a parabolic structure I should use. And then my moduli space is going to, the coordinates on my space are going to be these A's. I don't get any coordinates from the parabolic structure because we haven't, everything is equivalent. All vectors are equivalent. But I do get these variables now. So these are going to be my position variables. Okay, so now let me actually call them Q so that this is reminiscent of classical mechanics. Okay, and so now, what is my Higgs field going to look like? Well, it should have pole. So first of all, so phi is my Higgs field. And it's going to be, if I realize these bundles as trivial bundles outside of the origin by using these functions, I can think of it as, anyway, I can think of phi as a matrix phi ij, where phi ij is a section of LQI tensored with LQJ inverse. So this means, and I want a first order pole at z equals 0 and residue preserving. So this is L of Qi minus Qj, and residue preserving my vector 1, 1, 1, 1, and acting with eigenvalue c. This c is going to be immaterial. We can rescale it at the end, but I still want to keep it around. All right, so this means what? This means that phi ij, this bundle has only one section up to scaling, which is with first order pole at 0. And so this is just theta of z minus qi plus qj divided by theta of z. So here we should put some aij. And of course, this is when I is different from j. And then phi ii is a section of the trivial bundle. So this is actually just some pi, which is going to be momentum variables. Now, what can we say about this matrix? So in this case, we cannot have a pole. So what is the condition for the matrix A? So this matrix A should satisfy the condition that A111 equals to C times 1, 1, 1, 1, right? But then well, what is this? So this means that so the matrix A has zeros on the diagonal, and it should have rank 1 up to adding a scalar. So this means that all the entries of this matrix which are off diagonal should be the same. So A, I are 0, and A has only 2 eigenvalues. So actually, eigenvalue probably n minus n plus 1 times c, whatever. Anyway, so this has only 2 eigenvalues. So this means that all aij are the same. And A, if it preserves this line, then this means all eigenvalues, all elements are the same. So that's easy to check. And so what you get is that phi ij equals to some constant, well, let me call it c, times theta of z minus qi plus qj over theta of z. And so, so here is our matrix P, and this is Krichy-Verslax matrix for. Oh yeah. I'm sorry. Of course. Because I want a residue, right? And residue at 0 of this thing is going to be okay. You have to. This has derivative 1, and so I have to evaluate z, and so j minus q. Yeah, I don't normalize theta this way. Okay, so So I've got my matrix A, which is going to be, well, my Higgs field phi is going to be, well, P1, Pn. And here there is going to be this thing, constant, times theta of z minus qi plus qj over theta of z, theta of qj minus qi. And then you can compute the trace of phi squared. And this is going to be the sum of pi squared plus the sum over j different from I, so c squared times theta of z minus qi plus qj, theta of z minus qj plus qi, divided by theta of qi. This is an odd function, so this is just square. And so here maybe it is a minus, I don't remember. But in any case, what this is, again, everything now depends on this z. So as before, this is a generating function. And then there is a theta of z squared. So if you take, so you need to take some coefficient. So if you take a z inverse z to the minus 2 coefficient, you will get, well, this will evaluate to 0, this will evaluate to 0, you'll just get a constant. So it's not interesting. So the interesting thing you will get if you take the constant term of this Laurent series in Z. So the constant term is going to be the sum of pi squared plus c squared. And then the constant term is going, so this thing, actually, you can check. This is just the Weierstrass p function minus the Weierstrass function of qi minus qj. That's easy to check because this vanishes in the right places and has the correct poles. And so what you will get is that this is the sum. So the p function has trivial coefficient for z to the zeros. And so you will get minus c squared times the sum I different from j, p function of qi minus qj. And this is the elliptic Calogero-Moser system. So this is the quadratic Hamiltonian, which is elliptic Calogero-Moser system. And this gives us integration of this system because now we can consider traces of exterior powers of phi. And these are going to give us higher Calogero-Moser Hamiltonians. So this phi is it's Krichenver's lax matrix for elliptic Calogero-Moser. Huh? Or traces, well, phi is an operator, right? It's a matrix, so we can take traces with exterior powers. Or we can take traces of powers also, but that's less nice. Okay, any questions? That's it for today. And so on Friday, I'm going to explain quantum story.
Okay. Questions can be asked again at the discussion session. Lunch.
Спасибо, что ты исправил ошибку. Что я это самое не имел, мне не хватало времени смотреть сюда, и поэтому я.
Слушай, а вот Игорь всегда как-то очень подчеркнул тот факт, что его эллиптические роды это вот ровно, так сказать, не диагональные элементы этой матрицы. Я так не могу это самое.
Ну это вообще такая функция.
Я понимаю, да, но он как... Я понимаю. понимаем, но тем не менее, он как-то это самое. У него это как-то было вот, немного связь была как-то пошутка, не могу восстановить.
На Киевский, ну ты неправильно говоришь. На Киевский может быть без проболевки. Киевский прикончит.
Нет, ты не будешь, там ничего интересного не будет, потому что она одна точка будет.
Матрица Бакстер Беларина.
Правильно, но там не будет динамики никакой.
Ну, может быть, и прав. Это не динамическая система, ты прав.
Да.
Это не R-матрица, но не динамическая.
Да.
Павел, зачем вы пишете про то, что у А только два собственных значения? И как мы делаем вывод, что А и Ж равны?
Но это значит, что значит, что происходит? Значит, вот можно взять, значит, тогда будет что? У нас, предположим, что у матрицы А на 1 равняется какое-то собственное значение. Да? И у нее есть еще другое собственное значение лямбда штрих, у которого multiplicity, ну да, его будем называть, минус лямбда на n-1, которая с кратностью n-1. Чтобы свет был нулевой.
Это не выражено.
Да, да. Тогда что происходит? Возьмем матрицу А минус лямбда как на тождественную. Нет, А плюс лямбда на n-1 на тождественную матрицу. Тогда что получится? Эта матрица будет иметь ранг 1, правильно? Потому что все эти собственные значения станут нуля. Вот. Значит, и у нее диагональные элементы будут вот такие. Но если матрица имеет ранг 1, то тогда ее все элементы имеют вид там, альфа и t умножить на альфа g.
Ну да.
Ну вот, и отсюда будет следовать, что у нее там все элементы одинаковые.
Так, можете, пожалуйста, объяснить, почему
На бета g, я прошу прощения. Альфа и t на бета g.
диагональные слагаемые в поле.
Да, кроме того, она вот этот вектор сохраняет. Что используя эти условия, можно понять всем элементами. Да.
Почему диагональные элементы
это степени свободы. Можно что происходит? Это касательно если мы двигаемся вдоль слоя, это единственное, что может менять, это пыль. Это надо проверять. Можно проверить, что это на самом деле это скручено. То есть это означает, что на самом деле слои это один единственный. Нельзя сказать, что это моменты между моментами не только. Но это не важно, потому что если мы избегаем момент на функцию то теоретическая форма не меняется. Это потому что у нас потому что мы делали редукцию вдоль орбиты, это означает, что должен быть орбиталь. Ну, опять, я завел пока мертвого деталей, суть в том, что мы делаем редукцию вдоль орбиты. Редукция вдоль орбиты это касается несколько книжек, которая называется Collision. Lecture from Collision. Вот этого там нет. Но там есть объяснение, как можно получить рациональную или геометрическую голову. Ну, причиняется тому, что если есть, но нам это сложно прочитать. Я не знаю, я из головы это рассказываю. Ну, вот будут спеть записки, вот Хенри все записывает, завтра будут записывать. Но тут надо просто много чего проверять. Z минус второй получается константа. Z минус первый вообще нет, потому что это черная. Z нулевой дает тебе только. А дальше остальные тоже будут константы, потому что это такая функция. То Но вся зависимость от Z, она направлена сюда. Единственное интересное, потому что вот это это все очень мало. Потому что мы хотим сделать? Мы берем коэффициенты, так что нам не важно, если мы поменяем координаты, у нас это как-то все-таки все равно мы пространство координат, которое мы будем получать, мы будем менять. То есть вопрос в том, какой мы память. Так что какой тип тензора, это зависит от сочинения. Да. Что там прибавится, но в любом случае, вот эта вот зависимость от Z, она вся запрятана сюда, и при всех нетривиальных соединениях Z, это как Oh, because we want residue to be AI. So what does residue? Yes, I forgot to write the vector. That's right. So we have notion of parabolic files and we have ordinary reduction, which we did with but in this case, if we did an ordinary reduction without this C would be 0, we would obtain a board. We would obtain a system with electronic sound PIC with a board. So to get something interesting, we need to do yes, it comes from. So it has to do basically from the presentation here what to do. So if you have a parabola, potential one of G1 P. So this has a regular functions there. It will be functions from the order of the Richardson formula. You know Richardson. You have a generic point in the uniform identical. So this is the parabolic string. And so basically, when you reduce, so that means that in order to get parabolic structure, parabolic you need to choose this from the Richardson order. Yes. Parallel for parallel, and then it is ordinary string. But again, the details of this solution are not important because we're working on the big order where it is at by So the big important order is an open set in the potential bundle of the flex. Now these orbits, the simple orbits, are not open sets in the potential bundle right? But they're open sets in the twisted potential. There is a notion of twisted potential. And so if you take a class in H2 on the base, there is a way to define twisted potential. Yeah, that would be wildly affiliation that is didn't have the time to talk about it. But for example, this way you can get periodic torque. You do P1 with two parabolic points, you do with two large points, but each of them you do second order torque. So then you can obtain each system system which we do for particular integration. For that, we could use find for example, for SN2, you will get the assigned order. Well, you will get maybe not assigned order. It's like with one variable. So find or topic will be assigned. No, that would be, for that we need to take a while the unified structure with the second. So this means that we will do reduction. So, well, they said that we have to evaluate at the point. And the kernel reduction, and then we do something along the point for the remainder. But here we would have to take not just value at the point, but derivative. So we have to take subgroup of elements which not only evaluate to 1 at that point, but also the derivative is 0. And then the kernel will be G COS squared. And then you need to do reduction along the orbit for this division. So there is a particular orbit which will give you this one. How to get affine product? Well, I mean, it ends up being equivalent to constant structure for affine for maybe there are some she's working on this right now. On some geometric. And also there is a talk. So there is a talk of the in the basic paper. Lecture of 16 birthday. Is a video, very good talk. Actually, all talks by him are very good, but this one in particular talks about yeah, so yes, I mean, it's so if
我以为回酒店是。
that would produce all higher order. So it's actually, so you have a group G of and there for every n there is a shortest set sequence, so there is a group G of C of T over T to the n. And then the kernel is T to the n. Exponential T to the n. Yeah. So these are elements of the group which vanish to order n more to the at the order. And so if you do reduction by this curve and then do some sort of orbit reduction for this, you will get the story of these fields having cobalt of order n. No. So in this case, n equals 1. So this means you get both order 1. Huh? So the reduction for this group is that we don't want along the one just here. But then after you've done that, you make reduction for this already. Well, it's so in the case of parabolic structure, the condition is that the element should end by 0. It should strictly preserve it. Like if you have three situations, it would end by 0. In the untwisted case, it should end by 0. In the twisted case, if you have an orbit, it should end by an eigenvalue. It still preserves it, but not strictly. Because it's a parabolic, so what are parabolic structures? There is points of so we have a and then we have parabolic structure is spinal line. But now we want to have we have still this model which is diagonal. So we want that to have 3. So that when you so when you add the parabolic structure, we want the symmetry to break down. So that means we need a vector on which the store x comes stable. Yeah, so that means it should not have 0 over. Because otherwise there will be space. But then, if it is such a vector, you can always add like some element that makes all entries one. So you have no 0 right. This physics. That's right. It doesn't trivialize. Analytic point. Yes, but I'm not. No, but it doesn't matter. What matters is that this bundle. Thinking about this bundle versus thinking about. So this function is a neuromorphic section of this one with the 0 and a on all terms. So if I allow 0 here and over here, I keep both 0 and then it becomes. And then this is what's known. Okay, so that's the exercise. Yeah, so you write something like and then and then I take e to the power e times theta theta c plus 8. And this is going to have a 0 at A, and it's going to have essential singularity at the origin. So this trivializes O of A on x minus analytics. Algebraically, you can analytically trivialize. Because it's a section with a simple at the point A, and no other singularity. But here it has essential singularity. We have to make this back because we want to make the function doubly frequent. But this is not doubly frequent. It is multiplied by exponential of 2 pi I. ，that's a non-vanishing section. It has a 0 as a point. Then it's non-vanishing. So what is the essence of this bundle? Is a function which has a 0 and we have a 0 at the point B, no other 0. So since it must have a 0, since it's required to have a 0, this function, even though as a function has a 0, as a section of the bundle, is non-vanishing at the point. That's right. Yes. Yeah. Yeah. Something like that, yes. It's a twisted case. In the twisted case,
And I mean, can we construct model G of Taiwan almost any requirement for isolate from that without any isolate?
well, then it would be not parabolic, but this would be with uniformity subgroup structure. So it's going to be not the PI, not the Borel structure, but U structure, where U is U. You can, yeah, there is a space like that. And this space fibers over the set of all lambdas, and the fiber over lambda is that one? Yes. What do you mean, trivializing analytics? It's a bundle. You switch this. Oh, instead of curves? No, instead of curves, 22 with this whole thing doesn't. I mean, there is no. Yes, that's.
It's not.
Yeah, it is that.
Yes, this is somehow called choose.
Yeah, so it's that one.
It's the property of
Well, they all express to each other, like shoot something like that. No, but it doesn't matter because Q is fixed, so they should just change it by scalar. There is also a product of 1 minus Q to the n, but this doesn't matter because the just change is better by scalar. It matters. It starts to matter if we want to consider modular properties. It depends on Q, which means we vary our relative. But here we're not.
Через 40 минут. Хочу, но могу сидеть послать ее. Я хочу спать. Я на последней лекции уже был ближе. Потому что у меня фокус. Пойдем тарелку почитать. Вот смотри. Ладно, сейчас. Бери руку, из-за этого кажется, что у тебя не работает. Бери руку. Кстати, ну кто-то видит с вами. Дима, пойдешь тарелку?
Да, говорю.
Смотри, вот что там не будет места. У-у-у. Вот хорошо.
Я то, что
Все будут заполнены, а все после сотни людей.
что вы делаете? Я не знаю, надо как. Да, я тоже думаю. Ну там да. Я вот это, кстати, про странно. Просто как ты говоришь, говорить платформу, 跟你说了6个月，但其实后来改了。对，对，不要紧，不要紧，不要紧，
反正9月份我会在。对，9月初我不在杭州，我在国内。这个好像最近对我来讲比较正常吧。早，还有半个。
что ты его не видишь.
Ничего страшного, появится процент.
Да, конечно. Он все время здесь. Очень ответственный человек. Это на моей лекции, кстати. Это очень все.
Жив?
Да. 8. Я пришла опять прям вот так. Да. Ну, он жив, ну, говоришь. Да, ну там такая жизнь, что я плохо ее понимаю.
Я думаю, за Москву в принципе.
В Москве вы очень хорошо сам понимаете.
Ты умеешь. Твоя сестра, конечно, там живет, если разговаривать. Я не очень информации мало.
Я читаю, но есть такой человек слухов. Я только слушаю. Несколько раз в неделю в разных местах. Он сам живет в Англии. Вы помните, какое дело Браун? Вот.
Вопрос как понял. Лучше мое. Что, неужели снимать фото?
Здесь транслируют на 4 телевизора.
Да.
На ТК. Я, конечно, могу позвать китайцев и попробовать это сделать.
Сигнал не хватит.
Попробуйте, не жалко.
Нельзя сделать, чтобы он транслировался только на один большой экран. Везде есть, и снимать тоже. У меня рука не телескопическая.
Somehow I asked a few people. They all seem to agree that you should make a big WeChat group.
Yeah, okay.
Ты у нас первый. Посмотрим, как привет.
I think whatever other not everybody.
Вообще,
Они пока сказали, что
вообще шикарно. А что проблема? Все на все экране.
мне говорят,
Ну ты первый, теперь у нас. Нет, они все недоступны. Убери, убери на это.
Yeah, I think actually I think that got way too good. As more like we change надо контроллер.
А какой security? 1, 2, 3, 4, 5, 6, 8, пропущено одно сообщение. 1, 2, 3, 4, 5, 6, 7, 8. Ты смотришь прямо на Видимо, девочка одна подправила.
Проверить потом. Здорово. Через HDMI вообще
Почти 33 у меня, 3D. Это не может быть 3D, но качество очень хорошее. Я вижу, там есть такие. Ну, нет, такое качество.
А вчера китайский язык у вас получается, что вы выучили сколько иероглифов за вечер?
Что-то не учили.
Вы умеете делать?
Ну, слушай, ну это я не знаю, как это так вот. Ну, занимались, что-то вы...
Слушай, а что дочки не приехали?
Ну, подожди, у них своя жизнь как.
А, нет, я понимаю, ну интересно.
Не, ну прикинь, подожди, ну они ведь взрослые люди.
Да я понимаю, нет, но все равно...
Не, ну это так далеко лететь.
Далеко.
Они... Он всякие свои. Не, ну мы их, конечно, очень звали. Ну, не столько сюда, сколько в Шанхай.
Ну, Таня категорически сказала, жарко, Китай, поеду.
Лешин сын, кстати, китайский, я удивилась, он учил в школе, Лешин сын, китайский, он понимает и действительно читает иероглифы в школе. Твой сын, на самом деле, меня удивил, он действительно читает.
Он хороший мальчик, но это самое, что китайский
Его
иероглиф.
зовут, его зовут Матвей, Батюшка. Я он себя удивил, он язык читает. Он понимает, он развивает.
Давай.
Что?
Повыше.
А где? Вот эта штука, ой, от тебя работает. Да.
Я уже понял, да. Теперь я подумал, я уже еле. Потому что они все равно сказать, что значит сечение будет решение раз управлять какая циклическая значит, мы сделали управление, что это я живу восьмой, это другой. Если в отеле, там ты не купаешься, потом дальше там живем тебе подают стебли, хоть какие-то омары, какие-то не кошерные, если ты не кошерный, то вот так. Да, он тебя выбирает. Не надо, я передергивал. Даже нормально, только ты хочешь, можно забивать, но ты надо найти человека, который более-менее надел руку себе, нам прекрасно, готовили там йогу, и, конечно, там открутил, там еще салат, там овощи хорошие, не знаю, овощи, все можно купить, плюс все там долго, там французский долго, в общем, я здесь просто, я не знаю, как готов, стоять с этой стороны.
Okay, so I think maybe we should start. We're very happy to have Alexei Borodin from MIT, who will talk on geometry of dynamo models.
Thank you. Thank you very much. I need to turn on the mic. All right. Thank you very much for the invitation and for the introduction. I'm very happy to be here. It's my first time in China, in Beijing, in Bimsa. Very interesting. Great suggestion. Thank you. Right. And I'm doubly happy to be speaking in the workshop dedicated to Igor Krichever. This work is closely related to him and to his work, and some of the things I learned from him, I wish I could give it for him, but maybe he hears in some way. So the workshop is about integrable systems, and there won't be any integrable systems for a while. They will show up, I promise, so if you don't fall asleep by about 25 minutes into the talk, they will show up, and then in a very essential way. So the talk is about Daimer models, and I'll start by saying what a Daimer model is, if this thing is going to work. And maybe it won't, at least this work. Okay, this I can do on my own. Okay, there we go. All right, so what is a Daimer model? One starts with a graph, generally speaking, an arbitrary graph, but in my situation, they will all be planar graphs. And then one considers perfect matchings of the graph in mathematical terminology, or Daimer coverings in physics terminology, which is a choice of a subset of edges of the graph so that every vertex gets covered exactly once. So these are two examples. They showed up in chemistry literature for the first time in the 1930s, to the best of my knowledge. You can see the title, The Statistical Theory of Perfect Solutions. They were very intensely studied for a decade maybe in 1960s by statistical physicists. Largely, it seems, in connection with the progress in the Ising model and related ones. In 1980s, another group of statistical physicists suggested that the Daimer models may be relevant for describing a physical phenomenon, which is pictured over here. These are actual photographs. You might not be able to see what's written here. These are actual photographs of helium at temperatures that are close to absolute zero, and the temperature decreases from top to bottom. And what happens is that crystals show up, they form, and if the temperature gets raised a little bit, then some of the faces of these crystals, they become curved and they become much rougher. That one cannot see here. So these surfaces, when they're flat, they're very flat. So the fluctuations from perfect plane are very small, but once they become curved, then the physics changes and then they become much rougher. So somehow these pictures have something to do with that, and I'll try to comment on that later on. And then since the early 1990s, as usual, mathematicians were late to the party and sort of started looking at these models, but I think found things that physicists might not have studied or maybe didn't care much about. I don't know. So what is a Daimer model? So I said what a Daimer cover is. A Daimer model, for me, is a way to choose a Daimer cover with some probability. So the simplest situation is that if your graph is finite, you look at all possible Daimer covers, and you consider them equiprobable. So each one has the probability 1 over the total number of Daimer covers. Right? And then this is so the typical thing probabilists like to ask is what a typical object looks like. If you sample one Daimer at random, how will it look like? What can you see? And so I will talk about this type of questions for a while before we make a switch to integrable systems. Now, I will only consider one type of graph, which is a subset of a square lattice. And furthermore, I will consider only two possible subsets of the square lattice, both of which are squares. So this is one possibility when the square has axes which are parallel to the coordinate axis. And this is another possibility to draw an approximate square in the square lattice with the sides at 45-degree angle to the coordinate axis. So this particular subdomain of the square lattice is usually called Aztec diamond after Jim Propp, who named this domain about 35 years ago. All right, so the basic questions then is that I consider a domain like that or a domain like that. I look at all possible Daimer covers. I put a uniform measure on them. And I want to know what the typical object would look like. Can I say something about the typical object? Okay. Now, it's awkward to look at pictures like these. You're not going to see much. So I need a better way to draw them. And so I'll say now how to draw them better so that we can actually see things with naked eyes, so to say. So the first useful tool is to note that this graph is bipartite, which means that we can split the vertices into black and white so that the edges always go between a black and a white vertex. And then we see that horizontal edges, if they're chosen as a Daimer, they come in two types. They can either go from white to black or from black to white if I look at them left to right. And similarly, vertical edges also come in two types. They can be either black on top or black on the bottom. Do I have that? Here is black on the bottom, right? So now what I'm going to do, I'm going to replace my dimers by the surrounding domino. You see, each dimer, so each edge of my graph can be covered by a 2x1 rectangle, which is like a domino that covers it. And so I'll do that, and then I'll paint those dominoes in 4 different colors according to the 4 different types of edges that I have. Okay. Now, please do ask me questions if they come up. This I'll be happy to entertain as many as you can ask. I don't have a particular agenda to finish and so on, so I'll be happy to answer. All right, so then now I get a picture which is a domino cover of my domain, and there are 4 colors. Okay, so now it's better to look at this with naked eyes. And so these 2 domains here, if I take them of size 100 by 100, and then I sample in some way, uniformly at random, a random domino tiling, then I get this picture for the first example and this picture for the second example. Okay? I hope if this is the first time you see it, and these 2 pictures are drastically different. There is chaos going on here everywhere, and there is a very clear, clean color patterns in the corners. Right? So this is a phase separation that occurs here. So over here in the corner, you just get blue domino. So that means there will be a brick wall in this corner and in this corner. So there will be brick walls in every corner up to a certain curve inside which the chaos happens. So this curve is usually called an Arctic curve because outside of it, everything is frozen. And in this case, it's known to be a circle. It's one of the first results about the Aztec diamond. So this would be the Arctic circle. It goes back to Elkis, Kuperberg, Larson, and Propp. Now, this is better. So we can see that there is some difference between domains. There's something interesting happening. So I emphasize if probability is not something you're used to, this is the picture of a typical dimer. So, if you start drawing dimers, you can spend 1 million years drawing different dimers, and you will always get these corners, right? Of course, there are also tilings here that will not have these corners, but the proportion of them among all is tiny. Okay, the proportion is smaller than exponentially small. All right. So now I need another tool. So I want to actually view my pictures, not just like this. This is better, but not perfect yet. I want to do one more step. I want to lift my pictures in 3 dimensions. So for that, I'm going to switch to a window that hopefully has animations. So what will happen is that, so I have 4 types of dominoes, right? And so what I'll do, I'll replace each of them by a 3-dimensional shape. And what kind of shape I use, I'll just try to show. Let me do this. I'll just, well, maybe this is good enough. So I hope you see the 3-dimensional object here. Right? So I took the flat things lying in the plane, and then I lifted them into a 3-dimensional, strangely looking pieces. Okay. And what's the benefit of that? The benefit is that if I now start with a tiling of an Aztec diamond, so this is an Aztec diamond of size 4, and if I replace every domino by that strangely looking piece, then they will together form a graph of a continuous function. Okay. So you see that the domino tiling becomes a bird-like graph of a function. And that's an equivalent language, actually. So this function is called the height function, and instead of looking at the flat picture, the domino tiling, I can be looking at these functions. Okay? And it's better because it gives us a more suitable language, actually, to talk about things. So here is the Aztec diamond of 400. So what happens if I lift it to 3D in the same way? And what will happen is that the circle will actually become a surface. Right? And so what this literally tells you is that almost all dimer covers with very high probability, once you lift them to 3D, will live in tiny neighborhood of the surface that you see on the graph here. So this is the law of large numbers, or the limit shape phenomenon. So this has been known for a while. Any questions so far? Okay, I'll keep going. Now, this model that I'm showing, the Aztec diamond with the uniform weights, this has been studied to death. This is a deep model that mathematicians have studied for 35 years, and pretty much everything is known about it. You know, what do I mean? What?
Success.
Well, that's a difference. So Andrei suggests I should have said was studied to success. That's also true, but I stand by my formulation as well. What did I do? Oops, wrong button. So as I said, everything is known about it. So I won't go through all the results, through all the things that are written on the board, but any reasonable question you want to ask about this picture, probabilistically, you can answer. You know, non-probabilistically, if you want to know the total number of domino covers of this domain, it's going to be a clean power of 2. You know, if you want to have a puzzle in the evening to solve, try it. It's not that bad. It's a very pretty fact. It's not easy to find a domain with the total number of domino covers being as simple as this number. Anyway, so you know, if you can zoom in different parts of the picture, you can go in the middle, go in the lattice scale, ask for various probabilities. You can go to the edge, see how the edge fluctuates around the circle. You can look at the fluctuations around the surface. All is very well studied with very nice answers. The edge is related to random matrices. The fluctuations here are related to the Gaussian, two-dimensional Gaussian free field, conformal geometry, and so on. Okay. Now that's not going. This picture is not going to be a subject of my talk, although I could have easily given a couple of lectures about it. If you have concrete questions later, please ask. I'll give references and stuff. Yeah.
It's L Bufetov, not A Bufetov, right? Alexei.
Where is Bufetov? This is Alexei Bufetov. That's correct. This is Bufetov Jr. Yeah. All right. So if I told you already that there's only one domain I'm interested in, and it's already been studied to success, then what is there to do? So what I will do now is that I will replace the probabilities on the dimer covers, right? So I started by saying that let's just look at the simplest possible situation when all domino coverings are equally likely. So I'm not going to make them equally likely now. So how do I modify that? What I will do is that I will assign weights to edges of my lattice. And then when I have a particular domino cover, what I will do is I will look at the edges that participate in it, and I will multiply the weights of those edges together. And this will be the weight of my domino tiling. And some of them may be larger than others, depending on whether they use favorable edges or unfavorable edges. Right? If all edges had weight 1, then I get the uniform measure. But now I allow my edges to have different weights. Now that's too much freedom. I need to restrict it somehow to be, well, for the model to be possible to analyze in large scale. So I will only choose finitely many parameters. So I will choose a piece of my square lattice of size k by L. In this case, it's 3 by 4. So I will pick some positive numbers on the edges of that piece, and then I will duplicate them periodically, up, down, left, right. Okay. So this gives me set of weights on the square lattice, and then I get a way of biasing my covers. Some of them will be more likely, some of them will be less, and I want to know how the pictures will change. Does it make sense? Okay, good. All right, so here is an example. Do you know, is there a way to turn off this light and not the other lights? Okay, thank you for trying. I'll keep talking while you try. Oh, you actually, okay, wonderful. Thank you very much. This is, well, okay, my screen was not so perfect, so I prefer to have it sharper. So you see, this is no longer, I mean, there is still the phenomenon of separating frozen and unfrozen regions, right? So this is a sample, okay? Just trust me, it's a sample. It's a separate story how one draws a sample, but it's very clean. One can do it perfectly. This is maybe 200 by 200. And so you see that there are now frozen phases in the corners as before. There is also some curve that separates it, some curve, certainly not the circle. And there are also strange regions that show up in the chaos, right? So inside here, there is like a big chaos and small chaos. Something happens there. Actually, if one goes into 3D, remember the hyperboloid type picture I had, the plot of the height function. So if I now do the plot of the height function and I look near one of these regions that look, the star-like region, then one will see that the height function there is approximately flat. It's very close to being flat. This is a magnification of it. So this is the relation to the roughening phenomenon, right? So there is an appearance of a crystal phase that happens here. There is a very flat piece with very small fluctuations. Now, it seems kind of strange that I was able to achieve the new phase by just modifying the weights. And all I did, I just took the weights on the lattice, I took a 3 by 3 square, modified the weights, duplicated, and there we go. So this is a key feature of the model that actually makes it interesting. Okay. All right. And this is just a zoo of pictures. So you can see that these are different choices for different periodicities. So this is a 2 by 2 periodicity, so 2 by 2 square with arbitrary weights, periodically duplicated. This is a 3 by 3, 3 by 3 again. This is 2 by 3, and this is another 2 by 3. And you see pictures become different. They change. And yeah. So it's a wonderful question. There are actually two questions in one. So one of them is whether there is a temperature parameter. And yes, there is a temperature parameter, and one can freeze this picture to success, to temperature 0, and that will actually make it so that the crystal phases will fill the whole thing. I might comment on it a bit later in the talk. And the second question was about about the free energy. Yes, there is a free energy, and furthermore, the free energy in this case is going to be a function depending on the slope of the height function locally, and I will talk about it later. So, anything else? All right. Okay. So the basic goal of my talk is try to explain that we know what these pictures are. Okay. So somehow we didn't, maybe 2 years ago. Now we do. In more than one way, to be honest. So, and the message of the talk is that the picture that you see here, maybe, yeah, well, I hope you see the picture, the colorful picture, right? So that picture is a picture of a Riemann surface in disguise. Okay, it's a strange way to draw a Riemann surface. Okay, well, with some fluctuations. Fluctuations can be studied separately, but the law of large numbers. The surface that describes the typical dimer behavior is a Riemann surface. So there is actually, so there are four, in this is a 3 by 3 periodicity. So this is actually, the Riemann surface is an algebraic curve of genus 4. I will say how to build it a little later. And in order to go to this abstract algebraic curve, well, not really abstract, quite concrete but it lives in the 4-dimensional real space or 2-dimensional complex space, just zeros of some polynomial. Now, in order to map it to the colorful picture with dimers, there is an intermediary which is called an amoeba. It's a notion introduced by Gelfand, Kapranov, and Zelibinsky a while ago, about 45 years ago, something like that. And this lives in the plane, in the 2-dimensional real space. And so the way one goes from the actual Riemann surface or the algebraic curve to the amoeba is that one takes the log map. So one looks at the logs of the absolute values of the two complex variables. That produces a picture here. And now this picture, the flat picture in the plane, is in one-to-one correspondence with my colorful picture. The ovals here, there are 4 ovals, compact ovals. They go to the 4 star-like regions over here. Now the tentacles of the amoeba, so these go off to infinity. These correspond to the tangency points of the Arctic curve with the boundary of the Aztec. So actually the picture doesn't, well, no, it does correspond, but you can't quite see it. So there are 3 tangency points here, and there are 3 tentacles on each side. But the picture doesn't have enough resolution for you to see it. And then the regions in between, so here it's dashed over here, and the more chaotic region over here. So there is a diffeomorphism that goes from one thing to the other. Okay? So the actual math that describes this probabilistic limit here is this classical algebraic geometry, which is the algebraic curves. Now, the rest of my talk will be to try to explain in some way why these arise. And it's not a very simple thing. It would have been known a long time ago if it were that simple. But it's not too hard either, and integrable systems have lots to do with it. KL are the periods of my, 2 periods of my fundamental domain. Yeah, so that, right, so that's right. So if I had 3 by 3, then I have to have genus 4, so 4 ovals. All right. Okay, well, maybe before I go into integrable systems, this is just a cute fact. So I told you that there is a diffeomorphism between these 2 pictures, and so not only there is a diffeomorphism, but the slope of the tangent line under this diffeomorphism for the boundaries is the same. This is color coded, so you can see that when you go in this red thing going from lighter to darker, that's traveling in the Aztec, and this is traveling on the amoeba in the same color range. The diffeomorphism will map things with, points with the slope of the tangent line to points with the same slope of the tangent line. But the orientation will change because clearly the 2 pictures are different. So here you'll go counterclockwise, and here you'll go clockwise. And so the tangency points here will become the inflection point, well, the cusps over there. And that also sort of explains why the smooth ovals on in the amoeba will become these star-like regions with 4 cusps, because that's what will happen when you change the orientation on the tangent line, because you're introducing a defect of 4 pi, twice 2 pi. You're rotating in the wrong direction. So you add 2 pi and 2 pi, there is a 4 pi change, and that needs to get compensated by the flip of the direction of the tangent. Just a little bit of a, that's actually a proof that every domain, so every star-like domain over here will have 4 cusps. Okay. All right. Okay. So now, yeah.
Is it possible to think of this duality as sort of Legendre transform?
It's a generalization of duality of line proof.
Oh, yeah.
This is not literally well, you go.
In principle, you can have 2 curves in the plane.
Yeah.
We can form the locus where the shift of one is tangent to another. If one curve is the line, that will be dual, and in general, it's some transform.
Thank you. Okay, so now I could have skipped the next 2 slides, but I don't want to do that because the upcoming talk by Sasha Babenko will actually rely on some of the same things as well. So it's not so bad maybe to repeat them twice. So how does one go from dimers to Riemann surfaces? Okay, so one path, which is a well-established path in statistical physics, is through a variational problem. And that path actually proves that there must exist a limit shape for a problem like that. So no matter what boundary conditions you choose, you will always get this limiting surface that shows up. And that limiting surface is a solution to a variational problem. So what kind of variational problem am I talking about? Okay? So well, let me take an example. So here is my limiting surface, my limit shape. And what I know is that in the neighborhood of this limit shape, there are lots of different possibilities for my height function, more than anywhere else, right? This is exactly the shape that maximizes the number of possibilities in a small neighborhood of it. Right? So let me try to count how many possibilities I have in the neighborhood of some surface. Okay? So what do? I'll take my surface, oops, that's wrong. I'll take my surface, I'll cut it into little pieces so that each piece is approximately flat. I'm assuming that it's smooth, and it's going to be smooth almost everywhere. Okay, then in each piece, what I'm going to do, I'm going to freeze my height function on the boundary of the piece and count how many possibilities I have inside that piece. Because then, in order to know the global number of possibilities, I'm just going to multiply them between the pieces, right? Because on the boundaries, they will automatically agree, and then inside there is freedom. Now, because each piece is approximately flat, that problem is actually solvable explicitly. So that's the question that I started with. When you have a square in the plane with sides parallel to the coordinate axis, one can actually compute explicitly the number of dominal covers of this thing. This is the formula here. It doesn't look like it's an integer, but it's an integer. Okay, it's a discrete Fourier analysis computation. It's very nice. And so one can do it for, so the square, actually, if one goes to the height function, it has flat boundary conditions. The height function on the boundary of the square is 0. So you're computing the number of possibilities with the frozen flat boundary conditions. And in general, one can freeze boundary conditions with different slopes, and one can still do the Fourier analysis computation. So one computes how many things you have on each thing, and then you multiply them all together, and then you send things to the limit. The pieces become tiny. And then once you do that, you get a variational problem. So because you're multiplying things that you know, well, when you take the log, you're adding them up. And you're adding them up means you're integrating them. And so that creates a variational problem, which is an integral of a certain functional on your surface. And that functional wants to be maximized in order to find the limit shape. Okay? So that principle will play a big role in the next talk, and Legendre transform and everything related to that. Now, to me, I will only maybe say one thing here, because this computation of the free energy of that functional that is being integrated, it's a wonderful computation due to Andrei in particular, together with Rick Kenyon and Scott Sheffield about 20 years ago. And that computation involves the algebraic curve. Now, what kind of algebraic curve that is? So here is a recipe how you compute the algebraic curve out of your weights of the dimer. So if you start with a fundamental domain, then you put it on a torus, and then one introduces additional variables z and w on the edges that intersect two particular cycles on the torus. And then one computes all possible dimer covers of that graph on a torus, adds them up. This is going to be a polynomial in z and w. Well, in my notation, it's going to be a Laurent polynomial. Doesn't matter that much. And that polynomial is, so if you equate it to 0, that's going to be an algebraic curve. And that algebraic curve is responsible for the asymptotic behavior of my dimer model. It's not supposed to be obvious or clear why, but that's just true. And what I wanted to say is that it's very explicit how to start with a dimer model and produce that algebraic curve. All right, yeah. So then one could say, okay, so while you have a function also, why don't you just maximize it, solve some sort of Lagrange equations and see what happens. So that's not an easy part. You know the variational problem, but you don't know how to find a solution to it or whether there is an explicit solution. And so to find an explicit solution, we had to do something else, which I'm about to come to. But once the solution is known, there is a wonderful upcoming work of Nikolai Babenko, Sasha Babenko, and Yuri Suris, that actually verifies that the solution to that variational problem is that whatever the formula is, it does the job. Okay? And that does not tell you how to find the solution. So if you go to other domains, if you change the boundary conditions, how do you find it? Well, I mean, you can try to guess, but that part hasn't been developed, and it's not quite clear whether that's going to be possible. No, this is the free energy. This is the formula for the functional. The exact solution is the plot of the height function. The exact solution is, you know, for example, this plot, the plot of this function here. Okay. You had a complaint.
Yeah.
Please.
But I thought if the boundary is frozen, you're ahead of time now. It's going to be some kind of algebraic curve solving this.
In the periodic case, I don't know that. And you proved it in the uniform case, that's fine. But in the periodic case, I'm not sure that's exactly known. And you may be right, I agree that this should be true, but I'm not sure it's a fact. Right, so how I construct the polynomial? Well, the way I construct the polynomial is I take this piece of the square lattice, I wrap it on a cylinder, on the torus. You okay with that? We get a graph on the torus. And then I modify the edges. I modify the weights of edges, some subset of edges, which are here in yellow, by multiplying these ones by W and these ones by Z inverse.
This is just the fundamental region, right?
This is the fundamental region, right? So this is a 3x4 rectangle that's put on a torus and then modified along 2 cycles. Right? Then I can compute the sum over all dimer covers of that graph of their weights. I can compute the partition function. The sum of all possible dimer covers of the weight of that cover. Now in each term, I will have a product of some number of W's and some number of Z's. So that's going to be a polynomial in Z and W. And that's the polynomial that defines the algebraic curve. Spectral curve is immediate. This is the recipe, yes. Anything else? Okay, good. So now I'm going to change gears. Okay, I'm going to go into the integrable systems part, and I'm going to try to tell you the heart of the argument that allows one to solve the problem, actually, to find the solution. Okay. Now that has nothing to do with probability, so to say. That's the whole point somehow. And if one just uses probabilistic tools, they're too blunt to give answers to such refined questions. One needs to use something more pointed. And so integrable systems, in this case, help. There is a part that I'm going to skip, which is the relation of the dimer model to a matrix refactorization problem. So there is a path that allows one to map random dimer problems in particular domains into something known as the Riemann-Hilbert problem, the problem of factorizing holomorphic matrix, holomorphic matrix functions into factors that are holomorphic inside, say, the unit circle and outside the unit circle. So that part I'm skipping. I'm just going to the part where one wants to solve a certain Riemann-Hilbert problem. One wants to move poles of a matrix-valued function. One sort of wants to split a matrix depending on the complex parameter into 2 pieces, where one piece will have zeros of the determinant inside the circle and the other one will have it outside the circle. But now forget about all these words. So here is a question that one can ask a student in the first year or whenever the linear algebra happens. Take 2 matrices. So here are two arbitrary matrices. They have, so Z here is a variable, is a complex parameter. Alpha, beta, gamma, delta, A, B, C, D are just complex numbers. Okay. So one takes these 2 matrices, one multiplies them, and then what I want to do, so then if I compute the determinant of this thing, it will have a 0 in Z corresponding to the determinant of the first matrix and corresponding to the determinant of the second matrix. Right? There will be a value of Z when the first one becomes degenerate and then the second one becomes degenerate. Now what I want to do, I want to write this matrix product as a matrix product of two other matrices so that the zero of the determinant goes from left to right. Okay? I want to swap the zeros of the determinant. That's all I want to do. Okay? And for 2 by 2 case, this is explicit. Okay, here is an answer. And there is an x here that's expressed in terms of my original alpha, beta, gamma, delta, A, B, C, D here. It's a nice birational map. The problem is it's not bilinear. And what I need to do in order to solve my problem, I need to iterate this map many times. Really just two matrices, two 2 by 2 matrices, and I want to run this thing many times. So what I do is I run this refactorization once, then I take two factors here, I place them back in the original order, I refactorize, place them back, refactorize, place them back, refactorize. I want to do it 1,000,000 times, and I want to know the result that comes out. Okay. Now, the beauty of it is that this problem has an explicit solution in this is in terms of theta functions. And this is this is explained in a beautiful paper by Alexander Petrovich Veselov and Eugen Moser from 1990 or 1901. And that's an offshoot, so to say, of the finite gap integration method of the integrable partial differential equations. And the finite gap method has been developed, in particular by Igor Krichever in the early part of his career. And he was one of the key players in the development. So what's the trick? So how much time? I still have time. Good. So how does one linearize this integrable system? What helps you to do that thing 1,000,000 times? And what helps it is that you can change the coordinates on your space in such a way that your map becomes linear. You're just going along a straight line. And then you can go 1,000,000 steps or 1,000,000,000 steps, who cares? You know where you are. Right? What's that magic change of coordinates? So the magic change of coordinates is a very well-known trick, method, maybe by now. First, maybe it was a trick. One needs to represent the operation that we are doing, which I'm writing here. So this is my refactorization, right? I had my matrix polynomial, 2 by 2 matrix. I had it in the form p minus times p plus, where minus and plus refers to different zeros of the determinant, right? Maybe one of them is inside the circle, the other one is outside. And so what I want to do, I want to put p minus and p plus in their one order. And then I want to refactorize them to put them in the right order. Okay. That's actually a conjugation operation. So one thing you notice right away is that under this conjugation, the determinant of your matrix doesn't change. Well, that's I said before. You're just permuting the zeros of the determinant. But not only the determinant doesn't change, the characteristic polynomial of the matrix doesn't change either under the conjugation. And so I can write that characteristic polynomial, and its coefficients are actually all integrals of motion of my system. And by equating the characteristic polynomial to 0, I get the spectral curve. That's the same spectral curve that showed up in a different way from the dimer model. Under this mapping, it's one and the same. And then, if I'm on my curve, so I have my characteristic polynomial, so my P of z minus W determinant vanishes. If the determinant of a matrix vanishes, it means that it has a null vector. So my null vector I'll denote it by psi. And so that psi depends on z and the W. In the theory of integrable systems, it's known as the Baker-Ahieser function in a more infinite dimensional setup. Here, it's just the eigenvector of the matrix. That's all it is. And the trick is that under the transformations, what you have to do is that you have to trace. So this here is a vector function. So this is a vector of size 2, depending on z and w. So it's a two-dimensional meromorphic function on the spectral curve. Its zeros and poles have to satisfy conditions known from 19th century. from early 19th century. And so one needs to look at how the zeros and poles of that analytic function, of both entries, or one of the entries, doesn't matter, one determines everything, change under my refactorization. The key thing is that if one looks at these zeros, they will go along a straight line. Now that seems like nonsense because those zeros and poles, they live on the Riemann surface. There are no straight lines on the Riemann surface. Well, I mean, there is, in a way, well, there are many straight lines. One needs to map the Riemann surface into what's called the Jacobian of that Riemann surface. There is a standard operation which turns the Riemann surface into a torus of dimension equal to the genus of the surface. And you can think of going around the holes on the surface as periods, and so those periods will create the Jacobian. The map in the case of the elliptic curve is given by elliptic integrals. And on that torus, on that Jacobian, the movement of the zeros will now become a straight line. So it's a tricky change of variables. And so eventually, to get the solution to your original problem, you will have to write it in terms of the theta functions of that Jacobian. So that's a multi-dimensional theta function and all that. So that's not so easy to plot. Although, again, in the next talk, there will be probably nice pictures and also an explanation of how to draw that. And Kolebabenko here knows a lot about how to draw these beautiful pictures. But anyway, I try to say what the idea is, right? Okay, and this slide is probably just an iteration. Yeah, it's a little bit more detail. So one looks at this null vector, which has two components normalized in some way, and then one looks at each of them carefully, and each one will have two zeros and two poles in this case. And it turns out that one knows where the poles are just from the structure, and one knows where. Right. And then there is a condition on all zeros and poles of any meromorphic function on the Riemann surface known as Abel's theorem that they need to adapt to 0 in the Jacobian. So there is only one free parameter remaining, and so one needs to trace that free parameter. And since one knows the behavior of 3 of the 4 singularities and one knows the condition on all of them, then one finds out what the 4th one is, and that's really the straight line that one is after. So that's really 3 lectures packed into 5 minutes, so that's not fair, but I just wanted to say what kind of technology is used in order to solve the system. Okay, now this is just a show-off slide. I wanted to put up other examples where the same technology of integrating matrix refactorization shows up, because it's very common. The QR algorithm is used millions, maybe hundreds of millions of times numerically to find eigenvalues of matrices. When one starts with a matrix, splits it into a Q and a DAR, an orthogonal matrix times a triangular matrix, and then if you put them in the wrong order and then do the QR again and you repeat it many times, and there is a theorem that typically you will converge to a triangular matrix on the diagonal, there will be the eigenvalues because that operation doesn't change the eigenvalues. A very stable way of computing the eigenvalues numerically, and also closely related to the total lattice. Now the pictures here are billiard in an ellipsoid, I guess. So if you, well, this is two-dimensional ellipsoid, but if you play the game in a three-dimensional ellipsoid, I think this was the problem that motivated the original introduction of theta functions by Jacobi. And so that kind of motion, a particular case of it is computing the geodesics on the Jacobian, because if you shoot your billiard in the tangential direction, this will be geodesic of the ellipsoid, and that was a very classical thing, and that's reducible to a matrix refactorization. And again, I'm going to refer to a beautiful paper of Moser and Veselov where this is explained. And then the third example, one way of integrably discretizing the rotation of a solid body, the earlier equations of free body with deflation. So this is really a very classical way of constructing integrable systems with exact solvability. And if you're curious and you have energy and wish to study it, I really recommend. It's a beautiful piece of mathematics. And somehow I learned some of it many years ago by talking to Igor and to Dubrovin, unfortunately passed away as well. And it basically lay dormant in my memory for about 30 years until it came to life in this problem. So, if you're intrigued and you have 30 years of your career ahead of you, by all means, learn it. It will help you maybe one day. Yeah, that's it. I will only say that it was a pleasurable thing to do. There are many possibilities to develop it because the problem is basically solved only in a single domain at the moment. There will be one generalization discussed in the next talk. So the original result that I talked about was posted about a year ago, and since then there were two proofs that showed up that were different. One is going to be presented in the next talk through the variational problem. The other one is also a verification argument by Cédric Boutillier and Béatrice Detillier, just posted maybe a couple of weeks ago. That also did not provide the derivation thing. So for now, the only derivation argument that exists is through matrix refactorization arguments that I presented. So integrable systems really rule in this case. Hopefully, as time goes on, people will learn to handle other domains. We'll see. But for now, this is all I have to say. So thank you very much for listening.
Questions?
Yeah.
You didn't say anything about Newtonian structure.
Alexander Petrovich said everything. In the general matrix refactorization situation, there is a way to write the Hamiltonian structure, and it applies. It probably applies here just as well. I did not do it. I did not have a reason to do it actually, but I expect that the same formulas will give an answer as well. I mean, the first integrals are just the coefficients of the characteristic polynomial, but if you actually want the coordinates, then that hasn't been done. I mean, but it should be possible. Yeah. Man.
About the tropical geometry, I mean, the theory of set seems to be quite close. No, tropical geometry can be formulated theory of set. Can you comment on it? Maybe later.
So I don't know what
Chip firing.
So okay, chip firing is also related to the tropical geometry in the sense that one can get tropical curves out of out of abelian sand piles. But thank you for the question. That gives me a reason to find an image that I did not show. This is not connected directly to sand piles, but this is directly connected to tropical geometry. So there is a way to introduce a temperature parameter to the weights in this model. It's an easy way. You just take the weights and you raise it to the same power. Okay? If you raise it to a huge power, you will get either huge weights or tiny weights. Okay? So you want to know what will happen when that power goes to infinity. Right? What will happen is that the randomness, generally speaking, will want to disappear from your picture, and you're only looking for a maximizing configuration. You're looking for one dimer configuration that maximizes your energy, right? Well, generically, it's actually going to be 1. But if you start with a uniform measure, you raise ones to the same power, you stay with ones. So you need some genericity assumption. So generically, it's a theorem now that we are almost done writing up. That what will happen is, well, you can see. So this here is what happens when you raise all weights to a large parameter. So what happens is that the curved things disappear. Your whole limit shape becomes piecewise linear. And what's on the picture here is an image of a tropical curve. If you've seen tropical curves are quite different. They have tentacles and they also have convex polygons inside them. So a tropical curve is like an amoeba. So amoeba is going to converge to a tropical curve. But the Arctic curve was actually an image of the amoeba under some diffeomorphism. So that's the image under the diffeomorphism. You see that the convex polynomials convex polygons turn into non-convex ones. And you get this nice tiling of a square by some polygons. And you can look at the three-dimensional thing. And so we do understand what that picture is right now. And it is a direct image of a tropical curve that arises by taking the tropical limit of the spectral curve. Tropical Jacobian varieties certainly exist and may be useful in some contexts. In our context, we actually do not need to do that. We could take the answer from the non-tropical case and take the limit of the answer already. We did not need to do the matrix the tropical analog of the matrix refactorization. Those certainly exist. There are ultra-discrete integrable systems that people study, like KDV. I didn't see the ultra-discrete analogs of matrix refactorizations, actually. If anyone has, I'm happy to take a look. But the tropical finite gap is certainly being developed by people looking at something called box-ball systems and ultra-discrete KDV and TODA and various equations like that. So that part of the world exists. I don't know it well enough, I guess. But in our case, we didn't need to go to the Jacobian and the tropical case. We could just take the answer from the non-tropical and directly pass to the limit. Yeah. Any periodic weights. Any periodic weights. 3 by 3 was just the example that I had. Where is my PDF? Yeah. Oops.
3 by 3, no, this is 3 by 4 is similar, relatively to each other.
No, I don't think it matters in this case. I mean, that's an interesting guess, but well, we don't get higher level. I mean, we're in generic situation. The non-generic case is actually probably quite interesting because so the pictures I'm showing you are all under the assumption of genericity. If weights are not generic, there are various coalescences that's going to happen that geometrically might be very interesting to study, but we haven't even touched that. I mean, that's it. No, it worked. No, this formula works fine. That's fine. You get 2 times 2 is 4. That's fine. So yeah, to answer the question, this was a 2 by 2 case. This is a 3 by 3. And one could, in principle, try to produce pictures of arbitrary periodicity, except for you need a really big computer to do it because you need a large resolution to act. Because this is not just a picture, right? There are tiny dimers there inside the picture, so one actually needs to do that. The computer should be able to do the computation, and so I think 4 by 4 is still reasonable on 500 by 500 simulation, but higher than that, it's becoming a mess. So again, Kolebabenko is a specialist. He knows how to do the computations well. Yeah. One of the weights equal to 1? Oh, you want the periodicity just to be in one direction. It's not too interesting. Well, you get a genus 0 case. And that case can be handled by, it's a rational curve, and that can be handled by the formalism of Schur processes, the founders of which are sitting right here. So this is Andrei and Koля, and that case was known since 2000 or 99 or something like that. So it's simplification, and it's doable by the symmetric functions formalism pretty much. Yeah. Vanya, everything is connected with everything. I don't have a direct connection to offer to you, no. I mean, not to me. Maybe you can explain that to me. But yeah, okay.
Okay, so I guess the next topic is going to be. I think there's no pause. There is no a short pause. 2 minutes. Short pause.
Действительно, надо поговорить. Ну, ты не исчезаешь, да? Смотри, с нами неизвестно уравнение, но они же... Интересно, давайте. Интересно, нормально. Ну, это все нормально. Так хорошо ты поработал. Другой бедный, конечно.
So, can you hear me?
Yes.
Okay, very good. Yeah, so it's reasonable sound, yeah. Okay. Is it a good connection?
Yes, it's nice.
Okay, very good, yeah. So, I'll start with this window. Can you see me now?
We can see you, but not your slides.
Okay, so I will check whether it will be possible to show simultaneously. Yeah, but I'm not sure because the system says that I have to choose one of those. Okay. Okay, can you see the slides?
Yes, yes. We can see both you and slides.
But not me, yeah?
And you also.
Okay, very good, very good. So then it's perfect. Very nice. Mm-hmm. So it's difficult to, in case of questions, yeah. So it's difficult to hear the questions if they're asked without microphone.
Yes, questions will be in the microphone.
Thank you.
You're obviously sharing this one, right? You are obviously sharing this one. No, you are. I can share. That's it.
That's the sort of the organizer's role, but this is not for the speakers.
I'm the
You're committed to 2 talks.
It's fine. It's okay. But then I'll be back in a minute.
Какой-то маленький прямоугольничек, назначаем веса как один, потом веса периодически распространяем.
Hello? Yes? Could you please sit? Sasha, can you hear us?
I can hear you, I cannot see you because I can see only my screen.
That's fine. I mean, hopefully everybody here will sit down now and we can start the talk.
Yeah, okay. Just let me know when to start.
I think the speaker is a bit too loud. Okay. So I think for the next talk, we're ready, and we're very happy to have Alexander Bobenko from Berlin, who will talk on dimers and M-curves, as you can see.
Okay, thank you very much. Can you hear me well? Yes. I'm very pleased to be at that conference, also virtually. So it's a great event, and I'm very glad to be at a conference dedicated to Igor Krishchevar because my research was very much connected to what he did, and he influenced my life. And the results I'm going to present today are also amazingly very much related to his works. And this shows us, of course, how deep his works were. So I will give a talk on our joint results with Nikolai Bobenko, who is in the room, and with Yuri Suris, who is not. So there are two papers. One exists and one will be existing in a week on dimers and M-curves and on limit shapes. So my talk is based on these results. So, and of course it's very convenient to give a talk right after Alexei, so because he explained a lot, and my talk will be essentially about the same things, but completely from different perspective. Yeah. So I will start somehow at the point where he ends. And we will come back to the starting point of his talk. So the problem we are going to consider is the problem with dimer models. And news here. So we are on the graph. We are considered perfect matchings, but all these things were explained very well in the previous talk. And so we are looking at the probability of dimer configurations. So the weights are defined on the edges. it's very important in this talk that these weights, the probability weights for the edges, are not all equal. They will be rather complicated functions, and I will explain how they are how they can be specified. So the weights on the but we are going to come from this Riemann surface theory to statistical mechanics, and therefore it's important to learn what is important, what is on the mathematicians, what is on the mathematics. So the weights which are physical are the weights on the faces of this dimer configuration, and they're given by this formula. And although physically all the weights on the edges are assumed to be real and positive, they can be complexified in a way that the face weights remain complexified. And this is a famous Castellan condition which prescribes us the sign of this face weight. It's real with this sign where n is the number of pairs of edges around the face. And if this condition is satisfied, then the model is physical. Yeah. So I will not go here into detail because, as I promised, we start with mathematics and then we'll come to results with dimer models. So what kind of geometry, what kind of dimer configurations we are considering? So we are considering bipartite graphs with white and black vertices. And then there are parameters associated to these weights, and they are labeled by these train tracks which are shown here in the picture. So we are interested in integrable systems, and these are the features of integrable systems. So here we see just one edge with two parameters, alphas and betas, associated to this edge, and also a face, how these train tracks are arranged around the boundary of this face. So now let us discuss the problem we are going to solve. So as in the previous talk, we will mostly consider the square grid lattice because that's the most interesting and also provides us with all essential properties of the models. So you simply consider planar bipartite doubly periodic graph. In our case, it's a square grid with white and black vertices with two sublattices, and one considers a fundamental piece of such a square grid and assumes that there are some periodic weights associated to the edges of this graph, of this lattice. These weights generate a so-called Castellan matrix, K, so the entries of this matrix are just these weights. And then what you can do, you can define the so-called spectral curve. So you see here in this picture, this is a fundamental piece of your weights. And then you put, you multiply the weights sitting here with Z, weights sitting on these edges with W, and this is your Castellan matrix with spectral parameter. So when you solve the direct problem for dimers, then what you consider the eigenfunctions of this modified Castellan matrix, because well, and look at Z and W that have a non-trivial function psi. So of course, in this case, the determinant of K should vanish, and this is the determinant of KZW is an equation for the spectral curve. So in this case, that's the way how you generate Riemann surfaces, how you generate spectral curves, just by considering of periodic weights. These are classical results and well understood. So the main object here, I'm coming to this inverse problem, will be the eigenfunction. So this eigenfunction was just defined. It's a function on the Riemann surface on the spectral curve. And the monodromies of these functions, how it varies when you go here from left to right and from right to left, are just these Z and W complex parameters, which you take from the spectral curve. So what is important here, what you can analyze analytic properties of this psi function on the spectral curve, just from this classical description. So, and this is a direct problem for diamond models. You have your weights, periodic weights, you generate Castanet matrix, you generate spectral curve, and then you consider the eigenfunction on this spectral curve. So, I will be talking about the inverse problem. So now you consider this problem from the right to the left. So, and this is the approach which is very much related to Igor Krichever. So you can now set up the problem in a completely different way. You say, I have a Riemann surface and a function with some analytic properties on it, with some prescribed analytic properties. You've learned about these analytic properties by analyzing the direct problem. But now you become a little bit more general, and you say, my data are Riemann surface and this psi function or some analytic data for this psi function. From here, you can construct this function explicitly. Yeah, there is an explicit representation for this function. And then when you know it, you can derive the formulas for the weights from there. This is an inverse problem, which is known as a Krichever scheme. In this approach, the weights you obtain are more generic. They are not necessarily periodic. They are quasi-periodic, but they include all these periodic weights. So, and let me just, I'm very pleased that here, so I can mention a paper which really influenced my life. Yeah. So this is a paper by Igor Krichever, where he came up with this Krichever scheme in 1977. Yeah. So I was a second-year student at that time, and that was one of the first, if not the first paper I read, scientific paper I read. So the paper was about the KP equation, which is written here. And this was exactly the case where this Becker here as a function approach was clearly formulated and invented. You start with Riemann surface, you start with some analytic data on this Riemann surface, and construct Becker here as a function, which has very special analytic properties. This is a function which is meromorphic on the Riemann surface beside one point, where it has an essential singularity of prescribed time. This essential singularity depends on parameters of this KP equation, and some Paul divisor. These are the data, these are Krichev data. So, and then this function, it turns out it can be constructed explicitly. There is a formula for this. And as soon as you have formula for this psi function, you can derive from there a formula for the solution of a KP equation. So that was the first case when this approach was applied to a general Riemann surface. There were several cases which were studied before by Matveyev, by Dubrovin, by Novikov. It was essentially the characteristic de Vries equation or nonlinear Schrödinger equation, Sine-Gordon equation. But that was the paper where Krichev's scheme appeared, and it became very, very influential because it can be generalized, it can be specified for various Riemann surfaces, and it was the way how you can generate many integrable systems and obtain their solutions. So in a way, what we do with these diamond models, we apply this Krichev scheme to diamond models. So diamond inverse problem, and this is Becker-Hesse function. I believe that you've learned a lot about this function in lectures of Samuel Gruszewski. Yeah. So in a way, my talk is between his lectures and the lecture Alexei just has given. So what are the data? So we start with Riemann surfaces. We have a compact Riemann surface, and on this diamond graph, we introduce train track parameters. Now, these parameters, alphas and betas that are labeled of these train tracks, they're just points on our Riemann surface. Then you construct a meromorphic function on the Riemann surface, this Becker-Hesse function, with prescribed analytic properties. This function is defined at all black points of your graph, and the analytic property is the following. As soon as you cross a train track, then this function psi picks up a zero or a pole. So it's a meromorphic function on the Riemann surface, and its divisors are well defined. So as soon as you have these analytic properties, you can write a formula for this function, which is quite similar to the formula of Krichev in the KP case. But now the function is meromorphic, and such formulas and such meromorphic Becker-Hesse functions appear in analysis of discrete integrable models. Yeah, so I will not explain all these ingredients. What are thetas? What are e's? Yeah, thetas are standard theta functions. E is prime form. But there is an explicit representation for this. So now, it turns out that these functions are linearly dependent. If I consider a star associated to a white vertex, so all neighboring black vertices, then there is such a Becker-Hesse function sitting at all these black vertices, and they are linearly dependent. You can see this just analyzing their analytic properties. And exactly as in the KP case, from here you can compute the corresponding coefficients, which are now independent of the point of your Riemann surface, but depend on these parameters alphas. And these are nowadays called Fock weights. There is an explicit representation for them, similar to the representation for the solution of the KP equation. So just an explicit formula for the weights. So as a side remark, yeah. So if you play this game just for a triangle, then you obtain this Dirac equation for 3 Becker-Hesse functions, and then if you write down this Dirac equation explicitly, you end up with a famous Fay identity. So in a way, it's also a very simple way to prove Fay identity. So I assume that this identity played a crucial role in the lectures of Samuel. So this identity is here. Okay, so now we are going in the direction of statistical mechanics. That was complex analysis up to now. And what is important, we would like to have these weights real and positive. And well, then what one can do? So one should specify the Riemann surface. It should become a real Riemann surface with an anti-holomorphic involution. And in this case, to get positive weights, you should take an M-curve. An M-curve is a Riemann surface of genus G with a maximal possible number of real ovals, G plus 1. So here in this picture, you see 1/2 of this Riemann surface. Yeah? So it's a simply it's a flat planar domain with two holes here. All the boundaries are around. You take two copies and glue them together along the boundaries. You get a Riemann surface, and this Riemann surface is your M-curve. Or you just make an inversion, which is indicated here by tau, with respect to one of these circles, x0, and then you generate the picture on the whole complex plane with the holes x1 and x2, and then you have r plus and r minus, 2/2 of your Riemann surface, and they're glued together into one compact Riemann surface, which is an M-curve. I should stress here that, okay, we end up with this picture for an M-curve. And I should stress here that this is not just a picture. This is not an illustration. This is a Riemann surface, what you see here. So you have circles, you have centers of these circles, you have radii, and these are real parameters that define you the complex structure on your Riemann surface. The complex coordinate here is just this complex coordinate z. So you identify the screen of my laptop with a complex plane, and the complex coordinate on this surface is z. So this means that it's not only an illustration, you can make computations with these pictures. And that's exactly what we did. And I maybe should emphasize that all figures in this talk are not just hand-drawn. They are computed. There will be several figures here. Okay, now we've learned what is an M-curve, how one can uniformize it, how one can represent it in a way that is numerically treatable. And all these train track parameters, which you remember were the points on the Riemann surface, they are now, they should sit just on one of these real ovals. So, for example, on this real oval x0, on the unit circle. So if you choose these alphas this way, then all the phase ways become real. This is a reality condition. But we have one more condition, that the sign of this real number of all these ways should satisfy the Castellan condition. And this is the ordering condition for these points, alphas, on the real oval x0. So in general, this condition was investigated on minimal graphs by Boutillier, Cimmassoni, and Detillier. For G equal to 0, what we get here, we have no x1, no x2, just x0. And for genus equal to 0, you end up just with isoradial weights. So that's the case which was investigated and solved by Kenyon and Okenko. Okay, so but now let us come back to our square grid, simplify the picture a little bit. And that's the picture in the case of the square grid. So we have these train tracks parameters alphas plus and minus, and train track parameters betas plus and minus. And then if you look what is this Castellan condition, then you get this result at the right-hand side. So as I said, all the points on your Riemann surface should lie on one real oval. I mean these train track parameters. You see them here shown in colors, alpha minus, alpha plus, beta plus, and beta minus. And moreover, they should be clustered in such a way that all beta minus, all beta plus, all alpha minus and alpha plus belong together. They are not separated by other points. And moreover, these four sets, they are ordered in the way how it is shown here. So alphas separate betas. Alpha sets separate beta sets. And then your weights are positive if and only if the corresponding Riemann surface is an M curve, and the labels are chosen satisfying this clustering condition. So the same thing you can do on the hexagonal grid, which also hopefully will appear at the end of my talk. And then you have obviously three different kinds of train tracks, alpha, beta, and gamma, and they should be also clustered in a similar way. All alphas belong together, all betas and all gammas, like in the picture you see here. So this means that what we are doing here, it's not just complex analysis, this is statistical mechanics, because all the weights satisfy this positivity property. Good. So, and now just let me show the formulas you obtain this way. So these are the formulas for the phase weights. They are expressed in terms of theta functions. What is involved here are these train track parameters and integrals on the Riemann surface between the corresponding points on the Riemann surface. Yeah, so maps like the integral of Abel map from alpha I to beta I and stuff like this. Yeah. So these prime forms, which appeared in the formulas for the Fock weights, disappear in the formulas for the phase weights. So if now you do some computations, and I promised you to explain that how it is possible, so then you obtain pictures like this, and these are the phase weights on square grid diamond models. So in the case of genus weight, genus 1, you obtain picture like this. In the case of genus 2, you obtain pictures like this. And we have seen a lot of such pictures in the theory of integrable equations. So if you want, you can see this as waterways, as interacting waterways, as integrable interacting waterways. In the case genus equal to 0, we again end up with the isoradial weights. So all functions become rational functions. We are on the Riemann surface of genus 0. If you are back to doubly periodic case, then you recover the spectral curve. It's a the result by Kenny Okkenkopf Sheffield, and the corresponding Riemann surface turns out to become a Harnack curve. So, but the ways we are considering here, and that's exactly the same case with Kricher solutions for the KP equations, are not necessarily periodic. They are quasi-periodic. They came from this linearization on Jacobi variety, and this linearization hyperplane or linearization two-plane can cross the Jacobi variety in such a way that we do not pass through the rational points, and then it's irrational. So in this terminology, you see our parameters are an M curve, and these points, alpha plus, alpha minus, beta plus, and beta minus, the weights are periodic if and only if these two divisors, alpha minus minus alpha plus and beta minus minus beta plus, are principal divisors. So they are divisors of some meromorphic function. One should also mention that in the case when genus is non-zero, and even in the case when these train track parameters repeat periodically, the weights, these weights, the fork weights or the weights for the faces, are not necessarily periodic. Yeah, but they are quasi-periodic, and in this case, you can obtain similar results as in the periodic case, and I will explain this. Yeah, so they appear quite natural in this approach when you start with the Riemann surface. Okay, so that's what kind explains to us what kind of models, diamond models, we are considering. And now let us go a little bit more in detail into this algebra geometric description, which appears here. So the goal is, as Alexei has explained, is to describe limiting objects in the treatable form so that we can really compute the corresponding characteristics of diamond models. So in this case, we describe them using these algebra geometric terms. Okay, what are our data? These are so-called Harnack data. It's an M curve with an anti-holomorphic involution, tau, which I have explained already. In this picture, it's a reflection with respect to the unit circle. And with parameters, with points on our Riemann surface, alpha plus minus, beta plus minus, that satisfy the clustering condition. So, okay, again, the data you see in this picture, they're real data. So you just take this point, take this Riemann surface, and compute. Okay, now one introduces two normalized meromorphic differentials with simple poles at these points, alphas and betas, with residues equal to plus minus 1 at these points, and its zeta 1 has singularities at alpha plus minus, and its zeta 2 has singularities at beta plus minus. They, of course, are defined up to holomorphic differentials, but you normalize them in a unique way, just requiring that the A periods, all A periods vanish. And A periods on this Riemann surface are circles going, or cycles going around these circles. So these differentials are well defined. Now you take such a differential and integrate it and obtain an abelian integral. And since these periods, the A periods, vanish, this abelian integral is well defined on this 1/2 of our Riemann surface, on R plus. You just choose your starting point, starting integration point, and then it doesn't matter how do you integrate. Yeah, so it's well defined up to a constant. Okay, now we have two differentials, and we have two integrals, two abelian integrals. Let us denote the real parts by x's and the imaginary parts by y's. And then we are back to one more recent paper by Igor Krychev, who has considered this case and who has proven that these coordinates, if you take two x's, x1 and x2, or y1 and y2, they can be treated, their coordinates, on the R plus without the boundary. So that's this 0 here. Yeah, so this open set. So you can use x's as coordinates on R plus, or you can use y's as coordinates on R plus. And for some historical reasons, s's which are almost y's are canonically used in the doubly periodic case, therefore they will appear both y's and s's, but it's almost the same thing. So now we have two coordinates on this R plus Riemann surface, and we end up with the following picture. So again, this is our Riemann surface with the data. X's are well defined here, and there is a diffeomorphism of x's to some subset of R2, and the image of R plus is the amoeba. On the other hand, if you consider s's or y's, which is more or less the same thing, you map the interior of this disk, or R plus, to a polygon, which is called a Newton polygon in the periodic case. So these boundaries are mapped to 2 points inside Newton polygon, and they are mapped to some internal inner ovals of amoeba, so as shown in this picture. Again, this is a computed picture, so this is exactly how it looks like. Okay. So now, what can we do with this? Yeah, how one can use this? First of all, we are going to define Ronkin function and surface tension. They are both very important in variational description of dynamos. The Ronkin function is free energy, as Alexei has explained, and surface tension is a functional which should be minimized to get this height function as a solution of the corresponding minimization problem. So in this approach, one can obtain new formulas for Ronkin function and for the surface tension. So C1 and zeta1 and zeta2 are two differentials, that zeta1 and that zeta2. Zeta2 is an integral which is well defined on R plus. Zeta1 is differential. So you build such a product, integrated from somewhere to the point on your Riemann surface. This point has coordinates x1 and x2. And now you take the imaginary part of this, and this is a function. This function now is called the Ronkin function, and you play the same game with the surface tension function, almost the same thing. It's Legendre transformed, but treated in terms of other coordinates, not in terms of coordinates x's, but in terms of coordinates y. So they are Legendre dual, and they satisfy the following conditions. If you take gradient of sigma, then you recover the coordinate x's. If you take gradient of rho, you recover s's. So And this definition agrees with algebraic ones in doubly periodic case. So this case is, we are considering as more general. It's not doubly periodic. There is no spectral curve. There is only a Riemann surface. But if you consider doubly periodic case, then it's possible to show that this Ronkin function coincides with this Ronkin functions, which again appeared in the talk by Alexei, and which is due to Kenyon Alkounkov on Sheffield, where your integrate log of this polynomial of your spectral curve along a two-dimensional over two-dimensional torus. So with respect to x1, which is fixed by x1 and x2. So it coincides up to an affine function because you can show that the Hessians coincide, and fortunately, this affine function is not important for variational principles, because if you change rho or sigma by an affine function, it doesn't change your variational principle. So therefore, you can equivalently use this Ronkin function, or you can use this Ronkin function when you consider variational problems. So, and for our purposes, this one is much more useful because you can analyze the convergency and many other things. And this is an integral along the Riemann surface. Here, it's an integral over two-dimensional torus. Okay. Now we have extended this picture with two more maps. The gradient of rho is a map from amoeba to the Newton polygon, and gradient of sigma is a map from a Newton polygon to amoeba. So that's a dictionary. So in the doubly periodic case, you have a spectral curve, you have these functions z and w that can be treated as a monodromies of the Baker-Archies function. Main differentials are dz over z, dw over w, and the amoeba map is given by this formula. So in our slightly more general setup, we have an M curve, we have the monodromies of the psi function, we have two differentials, and we have this amoeba map, which is given in terms of billion differentials. Okay, now about height function. So, well, Alexei has explained that the height function is in bijection to dimer configuration, so you can analyze height function, and then this means that you analyze the corresponding dimer configuration. Boundary conditions are purely combinatorial deterministic, and it was proven by Kenyon and Prop that the limiting height function converges to a minimizer of this integral. So h is a height function, sigma is a surface tension, you minimize this integral, and then you get the answer. So we are in a more general situation with with quasi-periodic weights, and sigma is defined as a slightly different weight, but we were able to prove that this is still true for quasi-periodic weights, which are used in our approach. So the limiting height function is again a minimizer. So how does this minimizer look like? Yeah, so this is of course the most important problem. And as Alexei explained already, jointly with Thomas Berggren, they gave answer for periodic weights for Aztec diamond. So we will have a look on this problem in this slightly more general approach. And we were able to give another proof of this, which is purely variational, which is based on this variational description of limiting height function. And also, well, of course, it's very interesting to generalize this to more general boundary conditions, and in some case, this you can do also, as Alexei also has said, it's not an automatic thing. You should invent something. You should guess some analytic properties, or it's some creative work anyway. Okay, Now we will extend this general picture, which we will have, to include dimers, to include Aztec diamond. So the first definition of complex structure on dimers was obtained in the work by Kenyon Aukenkopf, which is 2005. But for us, a very crucial result is due to Berg and Borodin, who have considered the following integral. So d zeta 1 and d zeta 2 are two differentials, which I have already defined. U and V are parameters on the Aztec diamond. And d zeta 3 is a differential which is responsible somehow for the boundary conditions. So if you look at analytic properties of these differentials, then they are chosen as follows. D zeta 1 has singularities at alphas, d zeta 2 has singularities at betas, and d zeta 3 has singularities at all of them, and it's not a linear combination of d zeta 1 and zeta 2, so these singularities are chosen in the following way. Yeah. So now you can compute the number of poles and zeros of this differential d zeta, which depends on u and v. Then from some simple consideration, you can find out how many zeros you know quite well where they are. And it turns out that around the two zeros which you do not know quite well where they are located, and these are so-called free zeros. So one can define a liquid region. This is a point in your dimer model configuration when these two free zeros lie. They have to be mutually conjugated, complex conjugated, and they lie in this Riemann surface R0 plus and not on its boundary. That was the result again by Bergen and Borodin, who have shown that there is a diffeomorphism from R plus 0 to the liquid region of the dimer model. And this is the definition of a complex structure on the liquid region of a dimer model, which which comes from the Riemann surface. So that now the picture is complete. You have an amoeba, you have the Newton polygon, and you have your dimer model. And at the center of this, you have this M curve and three diffeomorphisms, X, S, and UV, to amoeba, to Newton polygon, and to the liquid region of your dimer model. Okay. So, okay, this sounds a little bit complicated, but let me show how it works in the simplest cases. For example, for isoradial case, you can write these differentials explicitly, zeta 1, zeta 2, zeta 3, and then you get the parameterization of all these Arctic curves in terms of Wronskians of these quite elementary functions. This is, of course, not new. But now let us generalize a little bit. Yeah? So this height function was an imaginary part of this integral del zeta. So now let us take its real part, consider its real part as well. So h is defined as this integral, and you have the real and imaginary part. And then it's easy to show that the gradients of G and H are exactly X's and S's. They are mapped to the amoeba and to the Newton polygon. So we have seen this already partially. H can be extended affinely to holes and frozen regions. And theorem is that H is a surface tension minimizer. So again, you consider this surface tension functional in this general setup with Riemann surface. You minimize this functional and get H, which comes from here. Of course, it's not the way how you generate this H, not by minimizing this functional, but what you can do, you can prove that H defined in this way will be the minimizer of this functional, and this means that it's a solution of this dimer problem. Maybe I will say a few words about the proof later, but amazingly, you can consider the dual problem in quite similar way. So, and this G, which is a real part of this height function, is a magnetic tension minimizer. You minimize not the surface tension, but the Ronkin function. So, and play the same game on slightly different set of functions. And here you can prove that G is a magnetic tension minimizer. G, which is here. So that gives us two more arrows in this diagram. So now the diagram is complete. So there is the map to Hammurba, there is a map from dimer to Newton polygon, and these both are described variationally. So in a more general setup, when you have a Riemann surface shown here, you also can do all computations. All formulas can be effectively computed via Schottky uniformization of the M curve. Again, now this is your Riemann surface. Schottky group is a group generated by inversion in all these circles. This is a group. You sum over this group the things you had in the genus 0 case, and these are the formulas for these meromorphic differentials we have defined. They are given by this Poincare theta series, which can be computed. So now let me show you the result. So that's a picture for Aztec diamond. What you can do now, you can take this M curve, compute all the weights using this zeta function representation, and then model, simulate the corresponding diamond model, and you end up with these pictures. And white curves you see here, they were the limiting shapes computed as I have explained to you. Yeah, so you see they fit quite well. Okay, how much time do I have?
Just a couple minutes, maybe 5 minutes.
I can't hear you.
Maybe about 5 minutes.
5 minutes, huh? Okay, thanks. So the proof idea is minimize this functional. You consider the Euler-Lagrange equation and show that this H, which we have seen, satisfy this Euler-Lagrange equation in the liquid region. But it's not the end of the story. Yeah? So the problem is that the surface tension is non-differentiable. It has conical singularities, and then it makes some problems to prove that what you have obtained is indeed a minimizer. So you should treat generalized Euler-Lagrange equations in terms of subgradients. In the genus 0 case, this has been done in the recent paper of Astala, Duzet, Krause, and so on. And what we did, we have proven this in the general case of genus 0. So it's not quite obvious how to extend this function G to interior, to the gas region in this case, yeah, to the gas bubbles and frozen regions. But this can be done. It should be done in the following way, that the gradients of this function lie inside the corresponding complementary components of the amoeba. So here there is some work. So, and maybe at the end, very end, I will show you a couple of slides so that other problems also can be solved in a similar way. This is a hexagonal case. This is a picture of the Riemann surface. Again, this is the Riemann surface, not just the picture, which has holomorphic symmetry, which respects this symmetry of the domain. This is the genus 0 example. This is example of genus 2. And again, you see the map. Now our Riemann surface we are considering here is ramified covering of a Riemann surface. And these holes here, these round holes, are again mapped to the gas regions of our Dimer model, and there is a one-to-one map to the liquid domain. So maybe the last, that's a picture in the hexagonal case. Now our Riemann surface is a double cover. The weights leave on the factor of this double cover, and you have diffeomorphism to the dimer liquid domain here from the double cover, and diffeomorphism to the amoeba and to the Newton polygon from this factor where the weights leave. Yeah, so that's probably the last slide of my talk, which shows us that you can investigate also how these gas regions behave, how they can come together and become hexagonal. And this is the case of ramified Riemann surface, ramified covering. This is the degenerate case, and this is an unramified Riemann surface. So I just announced some results on these limiting shapes, but there will be a talk by Nikolai at another conference, and I hope he will be able to provide you with much more results and much more proofs. Yeah. Okay. So summarizing, I wanted to say at the end, yeah. So that this was really surprising for me. So how well this Krzyżewa scheme fits to the investigation of these Dimer models. And I was surprised to see that we've learned from him from his 2014 paper, where he has considered generalization for amoebas, also in this more general setup. So this is really an application of what Igor did to this Dimer model world. And I think this is just the beginning, yeah. So because, well, there is very beautiful mathematics. I don't know how interesting it will be for statistical physics, but it's clear that similarly to the finite gap integration theory, you can specify Riemann surfaces, you can specify your models, you can specify your boundary conditions, and obtain much more results. So the mathematics of Igor is, I think, very influential and very productive. Thank you very much.
Questions? You will need the microphone. Any questions? I think we also have a chance to ask Nikolai in person later.
Yeah. Ask Nikolai, yeah.
We will, don't worry. Okay, I think people are tired. Let's thank Alexandra again.
Okay. Okay, thank you.
Thank you.
It was a pleasure.
Спасибо.
Thank you.
Бурштинская докладчик? А то... Что? Бурштинская докладчик? Нет, нет, здесь.
Привет, привет, привет. А? Я хочу проверить чек мне установить. Можно проверить? Работает проект?
Подожди, подожди. Как сейчас? Подожди. Мы не прямо сейчас еще все делаем. Сама, пожалуйста, не делай пока ничего, ладно? Я просто жонглирую, как всегда, 10 вещами сейчас. Сейчас. Можно пока пойти на брейк.
Деньги дать за такси.
Так, отставь.
Деньги за такси.
Помоги, пожалуйста. На кино на вечер. Спасибо. Я не знаю, вы знакомы, не знакомы? Ваня, это Катя.
Там видно,
У него будка.